Hello, everyone. Good morning. On behalf of all the workshop organizers, I would like to welcome you all to the LVIS Challenge Workshop at ICCV 2021. Today, I will first give a brief overview of LVIS version 1.0, which hopefully all of you are familiar with, and then I will describe the agenda of today's workshop. So let's get started. Ideally, we want our computer vision systems to have the ability to recognize all objects around us. One can imagine that such a capability will be of extreme importance for any intelligent agent. There has been great progress in the field of image classification, where we can now classify thousands or even tens of thousands of categories. However, current object detection systems still operate in the regime of 20 to 100 categories. Our goal with LVIS is to take the community closer to the goal of making systems which can detect everything by providing a benchmark for this task. On the outset, this might seem like a trivial endeavor. We know deep learning systems have shown tremendous promise in a huge variety of domains with exactly the same recipe. The first step is to create a huge balanced dataset for the problem you care about, and then you just apply a deep neural network. Most balanced datasets are built as follows. You create a list of categories, and then you collect images for those categories. However, this process will introduce categories in addition to the curated list you started with, unless you limit your images to be iconic. In this graph, I'm showing the growth of discovered categories for COCO validation set of images. Note that COCO images were collected with 80 categories, but we can see here that they contain an order of magnitude more categories. Simply adding more images does not alter the long tail nature of the problem. We can see that the number of annotated images increases, the percentage of rare category decreases, but is still a significant fraction of total categories present in the collection of images. Hopefully, with these graphs, I have convinced you that the first part of the recipe, that is making a balanced dataset, is not feasible. A large part of the success of current deep learning methods could be attributed to the scaffolding provided by balanced datasets like COCO, Pascal, ImageNet, and many others. Our goal with LVIS is to move towards a setting which we believe is more realistic and matches the long tail nature of category distribution in natural images. In doing so, LVIS exposes a few fundamental scientific challenges. For example, of course, tackling the class imbalance, but in addition, even evaluation of these rare categories itself is a challenging scientific problem. In June last year, we released version 1.0 of LVIS. This version has more than 1,200 categories, 2 million high-quality instance segmentation masks, and all of 164K COCO images annotated. With that brief introduction about LVIS, let's go over the agenda for today's workshop. You can find the detailed schedule on the LVIS website. We have two amazing keynote speakers, Professor Judy Hoffman from Georgia Tech, who will talk about the impact of dataset and model bias, and Professor Linda Smith from Indiana University, who will talk about babies, bodies, and learning to recognize objects. This year, we have introduced additional metrics to tackle various issues in evaluating detectors on LVIS. Our workshop organizers, Achal and Bowen, have introduced new metrics to tackle these issues and will describe how we can fairly evaluate object detection algorithms. After the challenge result announcement by Ross, Daniel will provide a detailed analysis of where the best challenge entries still have room for improvements using the TIDE toolbox. We have some really exciting challenge entries which have shown amazing improvements as compared to last year, and we are excited to have these team present their solutions here. Finally, we will have a panel session about the new rules, metrics, and future of LVIS. With that, I'm happy to invite our first keynote speaker, Professor Judy Hoffman, who is an assistant professor in the School of Interactive Computing at Georgia Tech. Her research lies at the intersection of computer vision and machine learning, with specialization in domain adaptation, transfer learning, adversarial robustness, and algorithmic fairness. She has won numerous awards like NVIDIA Female Leader in Computer Vision Award, AI Minor Top 100 Most Influential Scholars in Machine Learning, MIT ECS Rising Star, and is a recipient of NSF Graduate Fellowship. Prior to joining Georgia Tech, she was a research scientist at Facebook AI Research. With that, Judy, please take it away.
Thanks, Agrim. You have to stop sharing so I can share.
I'm just stop.
Okay. All right. Hi, everyone. Thank you for joining us this morning or evening, depending upon where you are. Today, I'm going to talk about, before we dive into this LVIS challenge and talking about the latest and greatest methods in segmentation, I want to talk a little bit about dataset bias and how that can translate to model bias. So first off, let's think about the standard recognition pipeline. We start out by collecting data sets. These can be huge, lots and lots of data. Of course, LVIS, the topic of this workshop, is one such data set. We then need to annotate the data with the particular categories of interest that we're going to use in order to ask the model to be able to predict these categories at test time. And this is a pipeline that's so standard and so universal in our field that there have been lots and lots of benchmarks created, both for classification as well as detection and segmentation, including LVIS, which you're going to see a lot of results on later today. Okay, so once we have this pipeline set up, we have these data sets that are collected, we need some way to evaluate our performance. And usually what people do, of course, is take the data that we've collected and that we've annotated, take a held out test set from that same data set, and use standard performance metrics, accuracy for classification, and maybe we'll learn a little bit about newer metrics for analyzing segmentation results later today. But once you have these standard metrics and you have this held out test set, you can measure performance year over year. And of course, this is what we do. It's pervasive throughout the vision community. It's what we're going to keep doing. It helps us to measure progress year over year, to compare algorithms fairly across one another. But this talk is going to illuminate just some of the deficiencies in using this as the full picture. So we're going to start out by seeing ways in which models that are trained in this paradigm and only evaluated under one set of conditions might fail when these set of conditions change at test time. And then later in the talk, I'm going to highlight ways in which these kinds of failure can disadvantage different populations. So let's start with the ImageNet dataset. Everyone knows this ImageNet dataset. We know that as we improve performance over time, we got to the point where really there wasn't much more room for improvement on standard classification, using all of the labels, using all of our compute, using all of our high capacity models. But we can ask the question, what happens when we take one of these models that has very strong performance on ImageNet test set and ask, how well does this model work out of the box to recognize these same kinds of categories that we knew how to recognize in ImageNet, but on a slightly different data set? So for example, let's take this big ResNet model that was trained on ImageNet and had strong performance and ask, how well does it work when we try to recognize dogs in a YouTube video? And it turns out that that model, when evaluated on the frames in this video, doesn't recognize the dog at all. So we went from a model that appeared to work very, very well to one that's having catastrophic performance failure on a very similar, or at least to people, something that seems very similar kind of data. And this brings us to the topic of dataset bias, which is just the fact that when we collect a static set of data, there's going to be a particular bias in the way in which it was captured, curated, annotated. So the ImageNet dataset was collected by scraping sites like Flickr. These are sites where people decide to share still images with one another, And really, if you're going to share an image of a dog, it's very likely to be someone's pet. You're going to share photos of the dog's face. You're going to take a few photos and maybe upload the photo that has the dog close to center of the frames, nice photographic composition, nice lighting conditions, higher resolution. These kind of biases don't exist necessarily when you're looking at YouTube videos where people might upload an interesting action. And the actions are more transient, so you're not necessarily capturing the best quality videos because the action maybe only happened once. So you have oftentimes lower resolution, motion blur, and a wider variety of poses than you would have seen in that still image database. Now, this phenomenon of dataset bias has been talked about in the literature for a number of years now, and it goes beyond something like just ImageNet to video datasets. In fact, one of the first works that looked at this was this work called Unbiased Look at Dataset Bias from CVPR 2011, where what was done was the 12 most popular computer vision benchmark datasets at the time. These were all mainly for object recognition. Some of them had more scene-centric images, but most of them had fairly canonical images in them. So you might think, okay, well, all of these datasets are collected with the same type of bias towards classification tasks, and so they should be relatively similar. But in fact, the bias was so distinct in these datasets that researchers, especially us researchers who spend a lot of time working on developing models to perform well in these datasets and maybe staring at the images frequently, people could actually see sample images from these datasets and were able to identify the dataset that images came from. Now, this is particularly striking when you think about how many images are in these datasets. And of course, they programmatically studied this and found that you could train a classifier to do the same thing. So what this tells us is that these datasets have such an innate bias to them that they're distinguishable, even by researchers in the field just looking at a few sample images. And this bias that exists in the datasets, it's natural and it's going to be pervasive. Whenever you collect a static set of images, there's going to be, a fixed kind of bias in there that maybe doesn't match the way in which you're going to deploy your system. And these kind of idiosyncrasies to datasets, they can be things like capture and curation bias that I was showing with the ImageNet to the video dataset, but they can also just be that when you collected your data set, you cleaned it. You made sure that all the images were had nice lighting conditions. You made sure that nothing was corrupted. And when those assumptions fail, when you take a model that was trained on only perfectly cleaned images, and then you try to evaluate it on images that maybe suffer from compression artifacts or have some of those motion blur that I was talking about before, or maybe just have simple changes in brightness and contrast. There have been studies that showed that models that were trained under the clean conditions and evaluated under these corrupted conditions will degrade significantly as well. So there's a lot of different ways in which our data can change. And you might say, okay, well, why don't we just collect a bigger data set? Why don't we just have a data set that can capture all of the kinds of scenes that we might actually want to deploy our system in? But this is sort of a flawed assumption that we might be able to capture all of these different factors of variation. Let's take this example of self-driving. So we have these outdoor street scenes. Maybe we want to perform a segmentation task. So we maybe want to be able to label every pixel, similar to what's happening in LVIS. Most people do it here with semantic segmentation, although there are newer data sets that are starting to have instance labels as well. But even for semantic segmentation, which is presumably easier to label, these images can be pretty expensive. To collect the annotation for a single frame, it's $10 to $12. And then you start to think about all the sources of variation in this kind of data. You're going to have to collect images and annotations across all kinds of weather patterns, all different cities, different sensors on top of different kinds of cars, collected at different times of day. the number of factors can really explode. So to just take this mental model of we're just going to collect bigger and bigger data sets and encapsulate all of these types of variations isn't necessarily feasible, though certainly people are trying. People are definitely going to keep creating bigger and bigger data sets, and I'm not saying we shouldn't do that, but we should recognize that anytime we collect a static data set, there's still going to be things that are missing at test time. And we can ask the question, well, what happens if you're missing a piece of data, a type of data? So here's one example where, let's say we trained a model on primarily images from the fall or from sunny weather conditions. So here's an image of a driving scene from a simulator. We use a simulator in this particular experiment because we could control factors of variation like the weather patterns. So we trained a model on images that look like this from sunny conditions. And then we asked how well can they work if the appearance changes due to weather patterns, like having snow on the ground. And it turned out that that model doesn't work at all out of the box, despite having strong performance on the sunny conditions. And not surprisingly, the areas in which it fails are exactly what you would expect. It fails in the scene parameters that have changed. So the road and the sidewalk that now have snow on them is precisely where the model is starting to fail, and it's actually confusing it with other aspects that it knew about that might have been that color, like the buildings. So one way in which people try to address this problem, where you have these sources of bias or variation that exist at training time and differ at testing time, is through this algorithmic formalism of domain adaptation. And this talk is not really going to be mostly about domain adaptation, but I just want to give you a high level idea of what people do in this space. So in domain adaptation, the setting is that you have access to a large labeled data set. And we have these. We have ImageNet, we have LVIS, we have a collection that I highlighted earlier in the talk of lots of large data sets that we have collected and will continue to collect. So it could be a data set that's just like we've put a lot of effort into curating. It could be a data set that's implicit based off the problem statement, like images from a product warehouse where the goal would be to recognize these products in the wild. Or it could be simulated imagery where the labels are somewhat implicit. But in any case, the idea is that the bias that exists in these training data sets won't necessarily always match the bias that exists at test time. Again, that could be because you went from still images to video. It could be because you're now trying to recognize these same products from this product warehouse as they appear when someone snaps them on their phone. Or it could be that you're trying to translate your model from working in simulated imagery to working in real imagery, and many other scenarios as well. But overall, the idea here is we have labels in one setting, we don't have labels in the other setting, and we want to figure out a way in which we can reuse as much as possible of the model that was trained under one condition for use in the other condition. So what people do here, I'm going to give just a very, very brief introduction to this idea of domain adversarial adaptation. But what people do here is they will train a model on the labeled data set, the source data set. And then the problem, of course, is that because the bias in the source data set doesn't match the bias in the target data set, they'll seek to mitigate this domain discrepancy, which is usually measured by having a distributional distance or misalignment between the latent features of the two domains. And the way that they try to mitigate it is oftentimes by measuring this misalignment and optimizing so as to reduce that discrepancy. And one really popular kind of approach is to do this using an adversarial learning objective, which basically works similar to GANs. You're going to learn a domain classifier to see whether or not you can distinguish source and target features. And if you can distinguish them, it means that they're misaligned, they're far apart. And so then people will optimize in order to mitigate this by aligning the distributions or confusing the domain classifier. So this is a really common paradigm, and people use this in the adaptation literature. But this is a very specific kind of bias in data, and it's assuming that the bias that you experience at test time, you have many, many examples from. So even though you don't have labeled examples in this target domain, you have a lot of overall just instances with which you can compute statistics, and by measuring those statistics, compute the misalignment between the original labeled data set and your current target unlabeled data set. Okay, so I have given a lot of examples where bias can exist in models. The first one was curation. It could also occur because of weather patterns. It could occur because of sensor changes. The most obvious one being training and simulation and adapting to real, but it can also be different sensors on cars with different calibration parameters that cause appearance shift. And there are many, many other ways in which our data sets can be biased and cause performance loss when that bias shifts at test time. But for the remainder of this talk, what I want to focus on is another aspect of bias that exists in these data sets. And the bias that exists and that causes potential harm to certain people is demographic bias. So this can mean that there's a particular distribution of people that are represented in a data set that's used for training. And as a result, when that distribution changes at test time, when you try to use a model to perform predictive tasks for people that didn't appear as frequently in your data set, or environments that surround people that don't appear as frequently in the data set, it can cause underperformance for certain populations. And of course, this problem of underrepresentation of certain factors of variation or certain subpopulations is what we've talked about so far. And that's what has happened with these curation bias, weather bias, sensor bias. But when we think about it from the person perspective, when we think about these subpopulations and how they might be underrepresented in our data sets, this can occur in many different ways. So one such way that was studied by this paper in 2019 was focusing on geographic bias. So we look at standard object recognition data sets. What we'll find is that the images that we have in our data sets are not evenly distributed around the world. In fact, if we look at a few popular data sets, and here what's being shown is kind of the density of these images based off of the geographic regions that they were taken in versus the density of world population, you'll notice that all of our data sets are dominantly from North America and Western Europe. So that means that there are certain appearances, certain ways in which objects have different meanings in different parts of the world that are underrepresented in our data sets. Here's one example of what spices might look like in North America on the right-hand side versus what they might look like in the Philippines. So it's natural, it makes sense. If we only saw examples of spices on the right-hand side, you're not going to do a good job at recognizing what spices look like in the Philippines. And that's what this paper found, was that performance at recognizing standard objects from these data sets did very well in the regions that had high density of data and did poorly in the regions that were underrepresented. And this isn't just true with object recognition. If we think about some of these off-the-shelf self-driving data sets, you'll notice a similar trend. So cityscapes is really collected mostly, first of all, in cities, hence the name. And these cities are sprinkled around Germany. This Argo data set is collected in 2 US cities, Miami and Pittsburgh, and a similar trend holds with a number of other driving data sets. Now, again, this is very natural because it's expensive to collect these types of data. You have to drive around. And so you're not necessarily going to be capturing all parts of the world while you're doing this. But again, just like that very first slide, when we are evaluating performance of our systems only on these static data sets, we need to remember that this is really a predictive performance for a very small subpart of the world. And we did a study looking at, even within these data sets, there's a distribution over regions in which a system performs well or worse. This graphic might be a little bit hard to read, but this is just one city within cityscapes. So even though cityscapes has images taken from a number of different cities, what we can do is we can imagine doing more of a microgeographic study, so looking at local regions within a city and how performance might vary. And we found that there are some regions for which predicting AP on something like cars performed very, very well, and other regions where it was substantially worse, ranging from 0.6 AP up to 0.95. And again, some of the observations maybe make some sense, like it was more frequent to have worse performance in city centers and you had better performance on highways. Maybe there's some innate aspect to this, that where one is easier than the other, but it can also be due to where was the majority of the data captured in these data sets. And if we only focus on this aggregate AP metric, we're going to be ignoring some of these nuances, which can be critically important when you're imagining deploying these systems. So aside from pure geographic bias, you can also have other forms of demographic bias that relate to the appearance of people. So one of the earliest kind of major failure cases that we saw in the news here of like a big recognition system that was deployed in the world was this system back in 2015 that provided an interface for people to upload images and have labels. These were users who didn't necessarily have any object recognition background, and they were catastrophic failure cases based off of presumably not having a sufficiently diverse test set, which the system was validated. So to study this problem, first off, people needed to create a new benchmark. There wasn't even a data set that existed to be able to understand whether or not systems had these kinds of biases, because in fact, the systems or the data sets did not have access to sufficient annotations for a diverse group of people to be able to measure predictive discrepancies. So this one work called Gender Shades, the first thing that they did was collected a data set to study predictive discrepancies across the appearance of gender and skin type. And they had to they tried to control for other factors of variation, so they collected headshot photos of parliamentarians that are, fairly canonical pose. And the only thing that they tried to vary was this skin type factor and gender. And when I say skin type, what I mean was they used this Fitzpatrick skin type scale. It's a scale that was actually created by dermatologists. It relates to how easily skin can burn, so it's not necessarily created from a computer vision perspective. But roughly what they did was they separated into two broad skin types, types 1 through 3, they called lighter skin tone, and types 4 through 6, darker skin tone. And they just wanted to understand how a performance of these off-the-shelf systems might vary as you looked at these two populations. And because the existing data sets, this Adiance and AJB data set didn't have enough data, especially from darker female individuals, but also from darker male individuals, because there wasn't sufficient data, they couldn't even measure the performance discrepancy. So again, like I said, their first step was to collect this new data set so that they had, they could make some statistical claims and have enough data to measure these performance metrics on. And what they found was, again, probably not surprising to people who have been paying attention to the news, but what they found was that the performance, though it was near perfect on lighter skinned males, you had error rates as high as 34% on darker skinned females. So this just illuminates this problem in a very clear way, that if we have training data sets that have underrepresentation of some groups or some types of factors of variation, then you're going to have a hard time having a system that performs well on those factors later. And if we don't even have this data in our test beds, we may not know that this is happening. So going back to these detection type scenarios, we wanted to understand whether or not there was a similar performance discrepancy when we were looking at something like pedestrian detection and driving scenes. So again, driving scenes are already very diverse. It's already very complicated to collect all the sources of variation that you would need. Again, all the weather conditions, lighting conditions, all of the different cities and different sensors. So that's already a behemoth to try to collect all of those annotations for all of that type of data. But we wanted to understand whether or not there was a predictive discrepancy when we were thinking about these subpopulations. So we followed the gender shades work and used that Fitzpatrick skin type scale. And first step was to take an off-the-shelf self-driving data set and annotate images of pedestrians where the skin, enough of the skin was visible to be able to label skin type. So that meant a few things. It meant that we had to throw out all the really small people because you can't see any skin. It also meant that examples like this, where it's just not visible, needed to be thrown out. So at the end of the day, that's throwing out a fair amount of data, but we just wanted to understand for images such as this, where people are close enough to the car that you can see parts of their skin, and where we were able to do this in a reliable way, meaning that we had 3 annotations and there was consensus among them about whether or not they were in the lighter skin tone or the darker skin tone group. And once we did that, then we were able to have a subset of this BDD data set that was labeled together with darker skin tone and lighter skin tone individuals. And here's a plot of the distribution of the number of labeled instances, both in train and val, across lighter skin, that's shown in red, and darker skin shown in blue. The first thing to notice is that there is a very big discrepancy between the representation of the lighter skin and darker skin individuals in this data set. So naturally, based off of all of these examples that we've seen so far where we have bias in the training data, it's going to translate to predictive discrepancy in our model. And we measured an off-the-shelf model that was not trained on this data set, that was just trained on COCO, as well as a model that was trained on this data set for pedestrian detection, and found that in both cases, there was a difference in AP for recognizing pedestrians across lighter skin and darker skin individuals. So at that point, the natural question is to ask why. And the obvious answer, it would be to say that we have a lack of training data. Because we were not collecting this data set, we were limited in how much data we had access to. So we tried other techniques that try to approximate resampling. In this case, we tried things like reweighting. We also asked the question of whether or not there were other confounding factors, whether or not it had anything to do with the actual skin appearance or with something else. Like, did people, was there different behaviors that correlated with people that meant that we were seeing more or less of one of individuals of different skin types in regions that had high occlusion, like in crowds, or different times of day, and we're not able to, we consistently continue to find a predictive discrepancy even as we controlled for these factors. So overall, as we see that these kinds of bias exist, we need to understand how we might be able to go about addressing it and mitigating these predictive discrepancies so that our systems can work for everyone. And the first thing I want to point out is that even measuring that bias exists, especially when you're talking about protected attributes or different demographic groups, it can be time-consuming and costly to collect the data, even to measure whether or not it exists. And I mentioned that the gender shades work needed to collect a new data set. In order to measure, even do a small experiment on pedestrian protection, we had to label a data set according to, again, this is just one factor of variation. There's all kinds of other things. Geography might be something that's a little bit easier to study because oftentimes images are available together with GPS coordinates. But if you're thinking about all the kinds of ways in which data might differ, all the different factors, all the different things that relate to people, the list is pretty vast. And to annotate all of those factors on top of the expense of already annotating the pixels according to the objects that we want to label is probably not tractable. So doing this kind of post hoc auditing based off of some factors that people think up and potentially even enumerating those factors is a difficulty. That may not really be the right overall direction. And then again, I think we still need to understand whether or not the bias that we see in our models is simply due to a data set bias, meaning that there's just a lack of data for certain groups of people. And so that lack of data both at training and at test means at training time that our model can't adequately learn to predict on those populations. And at test time, it means that we can't even really measure with any statistically significant claims whether or not our system performs well or not, because there's just not enough examples. So going back to this idea of domain adaptation, where what we are trying to do is we recognize that there's some kind of shift in bias from train to test, and we'd like to figure out, is there any portion of the model that's reusable so that we can adapt it to have better predictive performance on this new test set? Well, the assumption there was that you had lots and lots of data in your new bias setting. You didn't have labels, but you had data. And if we continue to collect our data sets using the same sort of protocol that we do now, that assumption may be flawed when it comes to demographic bias, because we may not even have the samples, labeled or unlabeled. We may not even have the samples with which we can measure and start to mitigate this performance difference. So I'm going to very briefly, in the remaining time of this talk, highlight two works out of my group that are going to appear at BMVC. And they're both looking at different aspects of bias and fairness. The first one is trying to address this question of reducing the cost in order to measure or understand bias in a data set. And again, if you want to measure bias directly by first enumerating factors of potential bias and then labeling them, that is expensive and time consuming. It also is subject to its own form of bias. So when you ask people to label some of these factors, there can be inconsistencies with those labelings. And so you're now, in an attempt to measure bias, you're introducing a new kind of bias. And so it's sort of a messy procedure. So instead, we'd like to find a way, if possible, to automatically detect bias in a data set and then provide those automatic detections of bias. Now, these biases may or may not align to cultural biases. They may just be sources of model failure. But then we can kind of present them potentially to developers and users as an explanation of the ways in which systems are degrading right now. So this work, we call it unsupervised discovery of bias in deep visual recognition models. It's trying to address this challenge where existing solutions require you to manually define a protected attribute and then label your images according to that attribute. And this, again, this assumes that you have the capability of first and foremost enumerating the potential forms of bias. And secondly, that you have the resources available to label those forms of bias. And what we'd like to do instead is a form of unsupervised discovery. and suggest subsets of the data to a developer or user where the model is currently underperforming. So I'm not going to go into great detail into the algorithmic details, but it's mostly based off of off-the-shelf agglomerative hierarchical clustering. We form different groups based off of latent features that have been learned to solve a predictive task. And what we look at in particular, because these are images that have already been labeled for a particular predictive task, we can measure the system performance per cluster. And quite simply, what we want to understand is whether or not we can find clusters of data that have similar appearance and perform especially poorly according to the current model. So this is really focusing on clusters of data that have poor predictive performance, and it really focuses more on model failure rather than cultural bias at this point. But at the end of the day, what we have are a set of clusters where the model performs quite poorly and we can prevent them. We have some techniques for ranking these clusters and presenting a filtered set that's not too overwhelming or too large. And we can present these clusters to a developer. So all you need are the labels that you had to already solve your predictive task. And now you'll have a set of clusters where the model is performing quite poorly. So I'm going to show you one example output of this system. This was trained on the Celeb A dataset to recognize whether or not a person was smiling or not. And the dataset is available together with a number of attribute labels. We didn't use them for this because we were trying to do just assume that you had only labels for solving a predictive task and minimizing the amount of annotations that are needed to use this sort of system. But at the end of the day, we found clusters that vary between finding idiosyncratic artifacts like the cluster on the left, where there's this strange vertical artifacting effect that causes the model to mispredict whether or not these people are smiling. Shown in the bottom are the corresponding GradCam visualizations for images in these clusters, and you can see that the model is focusing more on that artifact when making its decision. But we also found other clusters, and in the paper there's a long appendix of lots of clusters if you're interested to see, where the model was focusing on alternative regions when making its decision, like the forehead, or we found clusters where it was focusing on the fact that people were wearing hats in order to decide whether or not they were smiling, and so on. And so this can be used even without asking people to annotate, is someone wearing a hat, or does someone have wavy hair, or is somebody have high cheekbones? And it can be used in other contexts that don't address faces. We tried it also out on COCO dataset. We used it in a multi-category setting, this wasn't detection, and found forms of bias here that had to do with co-occurrence. So things like mispredicting a bed when you saw a stuffed animal. And so you can imagine using the same system as an exploratory tool inside existing data sets and with existing models, only needing the annotations that you had for solving an end task in order to illuminate the ways in which the bias, and this could be correspondence bias or just like appearance bias, the way in which that appeared in your data set without necessarily having to think up, oh, could it be because I have some people wearing hats, or could it be because there's usually stuffed animals inside beds in this data set? So the ongoing challenge that we have, of course, with this kind of approach is that at the moment, we're mostly presenting clusters together with, we can do things like GradCam visualizations, but it's not immediately clear always, depending upon what appears in the cluster, what caused the performance loss. Sometimes like this, it'll look like it has to do with the fact that somebody is wearing a hat. But as with everything in deep learning, we need to be careful not to overinterpret the results, because when we see clusters like this and we see that the model is paying attention to the hat, we may interpret that, okay, every time people wear hats, you're going to mispredict, or the model is going to always be focusing on the hat. But actually, leveraging some of the attributes that are available in the data set, because they do have hats labeled, we can do a post hoc analysis and find the most similar in terms of feature space appearance cluster to this cluster where people are also wearing hats. And we found this cluster, which was not one of the biased predicted clusters from our system, but because it had high predictive performance. And these people are also dominantly wearing hats. It's a different kind of hat, but the system is paying attention to their mouth when making this decision. So further investigation is needed to be able to understand, based off of clusters alone, exactly what's causing the bias in the model. Okay, so as the last piece of this talk, I want to highlight one recent mitigation effort. So once you have discovered bias, either by manual labeling and investigation, or hopefully in the future by some sort of unsupervised discovery technique, we of course want to be able to mitigate it. And because when we're talking about demographic bias, we may not have sufficient data for all populations in order to use an off-the-shelf adaptation type procedure. We need a way to make adaptive procedures work for us, even when we have limited data. And one such way that we looked into doing this was by leveraging recent advances in visual transformer architectures. Visual transformers, of course, build off of transformers from NLP, and kind of the key component here is this attention head, which has both a query and a key matrix. Really, the only important piece here that I want to draw out is the fact that because you have this disentanglement into query and key matrix, it presents an opportunity for investigating whether or not bias persists more or less in different components of this model. And so that's what we did in this work, was we looked at visual transformer models, which also have these attention heads. And we were able to find that if we were to measure the query and key matrices or activations on in these visual transformer models for things like predicting smiling, not smiling, we found that there was a pretty wide discrepancy between the difference of query heads versus key heads. And this implied a mitigation strategy, which was to focus in only on the parameters that had to do with the query. And so we applied alignment-based losses, but rather than applying it to an entire large network with millions of parameters, we focused in just on the parameters that had to do with the query matrix. Again, due to time, I'm not really going to go into too many details, but we're just, the key idea here is that we focused in on a very, very reduced subset of parameters, such that we could do a targeted mitigation approach, even when we had limited amount of data. And I'll just present one brief result. I think I'm running out of time, so I'm going to have to skip some of the more nuances of this approach. Again, the paper will appear at the MVC and will be available if you want to read more details about it. But after we optimize for alignment on the query objectives, we're able to reduce the bias across a protected attribute, like whether or not people have high cheekbones or not. And as a result, we're able to substantially improve on measures of fairness or predictive discrepancy. In this case, we're looking at the difference in accuracy across groups of individuals that have high cheekbones or not high cheekbones. And we're able to dramatically reduce that bias while retaining overall performance on the system. Okay, so if we're talking about object detection systems, there's a number of different ways in which bias can occur that are even more dramatic than in classification systems. So aside from appearance, you now have context to consider. We, of course, still have this representation question, whether or not there's underrepresented groups. The X factors, co-occurrence, object size, If you're dealing with outdoor scenes, you have time of day, and the list goes on and on. So overall, while we're thinking about our forms of bias with geography, demographic groups, context, and more, one of my takeaways is just to make sure to keep these things in mind. And when you're looking at your overall performance aggregated over a fixed data set, remember that there are subpopulations within that data set or within the world in which you're going to deploy your system. And always think about ways in which we might be able to either discover or measure performance across the diversity of the world that exists. With that, I'm going to end, and we might have a minute for questions.
Thank you, Judy. That was a very interesting talk. Yeah, I think that we definitely have time for some questions. So people can feel free to either put a question into chat or to unmute and just dive right in. I guess while we wait for people to maybe think about questions, if they have any, I'll ask one. Okay, so maybe to put you on the spot, if you had one recommendation based on this research for something we should do regarding the LVIS challenge or data set in the future to either mitigate or better understand bias, what would that be?
Well, I think developing tools that provide analysis beyond a single number for the whole data set is helpful. So this can be like well-known forms of error in detection systems, but it can also be looking at subgroups. So in LVIS, maybe you already have annotations for things like geography, or maybe you already have other kinds of statistics that you can compute just about co-occurrence of classes, and finding ways to break the test set into subsets and measuring performance over each of those. That will already go a long way towards understanding failure modes of a system.
Right, yeah, thanks for the suggestion. Let's see, do we have any questions from the audience? Okay, so there's one in chat now. Having long-tail distribution of classes in a data set also a kind of a bias?
It is. Well, basically, the bias in the case of long tail is would be that the fact that the long tail categories, you still want them to perform well. So in any given instance at test time, you're even though we measure performance in aggregate over lots and lots of images, somebody that's using a system cares about how it performs like right now in this one image. And so if you're right now looking at mostly categories from the tail, that's already a very different distribution than what you had at training. And so if you are, again, looking at aggregate measures over all categories or all appearance types, that's not necessarily indicative of how the system will work at any given one point.
Right, thanks. Yeah, so I guess that's all the time that we have for questions. And thanks again, Judy, for coming here and giving that talk. I think these are really important issues that we haven't thought about enough in the past, certainly not at the time that we're constructing all this data set. And I think it's great to have the opportunity to have you present and at this venue and make people more aware of the issues that we should be thinking about. Okay, so next up, yeah, thanks. So next up on the schedule, we'll have an overview of the new metrics that were used in the LVIS challenge this year. And this will be presented by Achal and Bowen Cheng. So hopefully you're here and able to share your screens.
Yeah, I think we have separate presentations. Maybe I'll start and then Bowen, you can take over. All right, I'm gonna just give me a second. All right, can everyone see my screen?
Yep, looks good.
Cool. Yeah, thanks for attending the workshop and for staying for this talk. So I'm going to talk a little bit about some challenges in evaluating detectors for large vocabularies. And I'll do that by starting with a practical issue that shows up when you deploy these detectors, and why these issues require careful handling in the average precision metric. So one of the practical issues you see when you run large vocabulary detectors on an image like the one on the left is you get a bunch of overlapping predictions for different classes with varying confidences. Now, this is a little messy, so let's zoom in on one particular instance. We see here that the detector outputs two overlapping predictions for different classes. And this is problematic since it prevents downstream applications from having a clear, unified understanding of the scene. So if we wanted to resolve this ambiguity, we would need to compare detection scores across classes. We need to be able to say, do I trust this book prediction at a confidence of 30% over an umbrella prediction at 56%? And it turns out that our detection methods and evaluations don't actually require that confidences are comparable across classes. In fact, what I'm going to talk mostly about in these slides is that current evaluations actually can discourage properly calibrated scores. So this is AP old, which is the metric that was used in the past, can actually discourage proper ranking or calibration of scores. I'll start by talking about a toy problem to illustrate how detection evaluation works and what leads to this strange property. And then I'll show how this shows up in a real world example. So consider running a detector on this image. Let's say that the detector outputs a bunch of correct high confidence predictions for the 4 dogs on the right, and then one lower confidence prediction for the dog on the left with an overlapping low confidence sheep prediction. To evaluate these detections via AP, the standard detection evaluation requires ranking these predictions. Now we can consider 2 ways of ranking these predictions. The first naturally sorts the detections by confidence, and the second one artificially increases the score of the sheep prediction to move it to the top of the list. Now, ranking 1 is intuitive. It's just relying on the detector's confidence to sort from the most confident to the least confident, while ranking 2 seems arbitrary and strange. I've just made it up for this example. Well, we can take these 2 rankings and see how AP evaluates them. Now, in theory, the way AP works is that we split predictions per class and evaluate a precision recall curve for each of the classes individually. So note that this treats both rankings equally. This isn't great, but at least it's not encouraging bad rankings. But this is only what happens in theory. In practice, there's a small caveat. To make detection evaluations efficient, we impose a limit on the number of detections per image, which results in throwing out the lowest ranked detections. In this example, I'm setting the limit to be 5, but in different data sets, that limit can be higher, such as 100 in COCO or 300 in LVIS. This might seem okay, but it turns out that in large vocabulary settings, you can actually show that with a limit on the number of detections per image, AP can actually encourage ranking 2 over ranking 1, even though ranking 2 is an unintuitive miscalibration or re-ranking of the detector's outputs. I won't go into detail here, but at a high level, the reason this happens is that AP prefers that the detector outputs a new class that it has low confidence of being right, rather than getting another instance of the dog class correct. We work this out in the paper in more detail if you're interested. And we can go beyond this toy example. We can look at the LVIS datasets, and we actually can show that this kind of re-ranking, where you remove some high confidence detections and replace them with low confidence ones, can actually meaningfully improve AP. So here I'm showing a baseline model on the left and a re-ranking strategy on the right, which improves AP by 1.7 points under the old AP metric. So to fix this, we presented AP fixed, which was a metric used, which is part of the metric used in this year's challenge, which makes AP a truly independent per class metric. So what this does is it removes the detections per image limit and replaces it with a limit per class across the entire data set. So now detections never compete across classes. With this metric in hand, we can evaluate recent detector advances, recent at the time that this work was done, and see how much they improve over a baseline model under AP old and under AP fixed. One example I'll show here is we looked at how important the choice of loss function is for LVIS detection. On the y-axis, I'm showing the delta over a baseline ResNet 50 model, and in blue, I'm showing the delta under AP old, and in orange, the delta under AP fixed. Under the old metric, it appears that the choice of loss function is critical. You can get improvements of almost 2.5 points over the baseline. But under AP fixed, the improvement is much more marginal, suggesting that the loss functions may have been focused on modifying cross-category rankings and possibly gaming AP implicitly. So as a quick recap, these small vocabulary evaluations that we used to use don't necessarily suffice directly for large vocabularies. AP old can be gameable and can reward unintuitive cross-category rankings, while AP fixed, which we present, removes the impact of cross-category rankings entirely. This restores AP to its original goal of being an independent per class metric. What I haven't talked about, which you can look in our work, is AP pool, which is a different metric we present, which actually can also reward more accurate cross-category rankings. So if you're interested in calibration, this might be something you want to look at. And that's all. Thanks for attending the talk. I'll hand it over to Bowen.
Yeah. Okay, thanks, Achal, for the introduction of AP Fix. Now I will introduce one of the other new metrics for this year's LVIS challenge, which is the boundary AP. So boundary AP is proposed in our CVPR 2021 paper together with Ross, Peter, Alex Berg, and Alex Kirillov. And so our goal is to develop a new measurement to evaluate object-centric image segmentation, which provides a clear and more quantitative gradient that will reward improvements to the boundary segmentation quality. And the boundary AP is an application to the instance segmentation task. So why do we need a new metric? In the last decade, mask LU has become the standard metric for various image segmentation tasks, despite having some limitations. And in this presentation, I will use instance segmentation as an example to show the limitation of mask LU, as well as our solution to fix it. So we uncover the limitation of mask LU by feeding the ground truth bounding boxes to a mask RCM model to study the segmentation error in isolation of the categorization and localization errors. So although the model predicts a fixed size mask, which is always 28 by 28 pixels for all sizes of objects, the mask AP for large objects, as shown in this table, is significantly larger than that of small objects. However, upsampling the 28 by 28 mask to a higher resolution output naturally leads to greater error, as shown in these predictions from small, medium, and large objects respectively. The number of different pixels between ground truth and prediction increases, suggesting the boundary quality of these predictions decreases as their sizes becomes larger. Despite the decrease in the quality, their mask LU actually increases with their sizes. This suggests mask LU may have limited sensitivity to mask prediction errors near object boundaries. The root cause of limited sensitivity to mask prediction errors near object boundaries is that mask LU is scale invariant. As shown in this toy example of two circles with radius R1 and R2, if we scale the two masks by the same scale R, the mask LU does not change. However, the discrepancy between the red and blue circles becomes larger, as shown by the blue ring. And mathematically, it increases by a factor of R squared. However, the number of pixels on the boundary, which is the perimeter of the circle, grows linearly with this scale R. And this leads to the mask LU tolerating a larger number of misclassified pixels per each unit length of the boundary for larger objects. And in this toy example, we show that the error per unit length of the boundary of this circle on the right is R times larger than that on the left. This suggests mask LU tolerates more errors for larger objects than smaller objects. To fix the issue of mask LU, we propose a new measure named boundary LU. Now I will explain how it is calculated. Given a ground truth mask and a prediction mask as shown in this example of airplanes, we first extract the boundary regions of two masks respectively, as shown here. And we define the boundary region as mask pixels within a distance of d from the contour of the mask. And here the boundary region is illustrated with the blue and orange shaded region. And finally, we calculate intersection of ground truth and prediction boundary regions, as well as their union. And the boundary LU is defined as the ratio of this intersection and union. Boundary LU ignores inner regions, which usually contain correct predictions. This property makes boundary LU more sensitive to the boundary quality than mask LU. And more importantly, the boundary region does not scale with object sizes. And as shown in this example, these two circles has different size, but they both have the same boundary region. For small objects, this behavior leads to boundary LU behaving identical to mask LU, whereas for large objects, the boundary LU ignores interior region and focuses on the boundary region. Boundary LU can be easily applied to evaluate instance segmentation by replacing the mask LU with boundary LU in the average precision metric. We re-evaluate the same mask RCM model with our boundary AP. While mask AP increases as object sizes increase, boundary AP is showing a completely reverse trend, which suggests boundary AP is not a simple scaling of mask AP. And this observation also suggests that the new boundary AP metric aligns better with the visual boundary quality. For this reason, we decided to switch to boundary AP in this year's LVIS challenge to also focus on the boundary quality of mask predictions. And that's all from my side. Next, I will let Ross to announce the challenge results this year. Yeah, thanks.
Right, thank you, Achal and Bowen. I guess we have a little bit of time in between. So if anyone has a question about either of the two new metric changes, feel free to unmute and ask, or you can ask in the chat. So I'll just pause for a moment to see if there are any questions. Otherwise, I'll continue on.
I got one question concerning the boundary IOU. So I think we still use different IOU thresholds, right?
Yeah, that's right. So as in years past, there's still integration over multiple thresholds.
And there have been some analysis to show how well the labels of different annotators were aligned. in LVIS and in COCO. And so how do they translate from the usual mask IOU to this boundary IOU? Did you investigate this?
Let's see, I'll let Bowen or Alex handle that question.
Yeah, I think we did the analysis on the on different data set, and since LVIS, the annotation quality for LVIS is like very good. The consistency between different annotators on LVIS, the boundary LU is more than, if I recall this correctly, it's more than 19%. So it's a very high high consistency between the different annotator. Even we use a stricter metric like boundary LU.
Okay, thanks.
Yeah. So go ahead.
Maybe one other question to the changes in the AP. Did you consider to also use the real precision of the detectors in the overall rankings? So in the end, still, I think now you have a limit of 10,000 predictions for the also for the very rare classes. So there still might be a lot of false positives for these classes, which are not penalized. And what do you think about that, to maybe also include the precision, the actual precision of the detector in the end?
So I'm not sure if I quite understand the definition of actual precision in this context.
Yeah, so the way how AP is defined, it's always beneficial to use the whole limit. So you will you will always be better if you add a lot more predictions for your class, at least if they have a low score. And so in the end, you might have a really low precision for the rare classes. And this precision is actually not reflected in the AP.
Yeah, well, okay. So I guess maybe a different perspective is that this is just how AP is defined. Those detections at the very end are kind of irrelevant for AP. At that point, precision is 0, and AP doesn't get any additional credit for adding new detections. But I think at a high level, kind of philosophically, there is no one correct metric for any of this sort of thing. And in particular, there's always going to be a discrepancy between metrics that you want to use in real world applications and metrics that you use in evaluations like LVIS, where it's kind of ethereal in a sense and it's disconnected from any real world deployment. And I think this comes up in the case of where you're thinking about calibrating detector scores, like LVIS in particular with this fixed AP is sort of invariant to calibrations that don't change the ordering of detections within a category. This, of course, is not a property you want in a real world detection system. So I think there's going to be a disconnect, and ultimately it's hard to decide from first principles what's the right generic evaluation protocol for a challenge. Yeah, so I guess those are just a few thoughts about that.
I think that I just wanted to ask, because the reason I was asking is that often in the end, when we have a trained model and you want to ship it or you want to deploy it somewhere, then it's sometimes very hard to find a good threshold for your scores. And
yeah.
AP always, or in these challenges, it's beneficial to put the threshold basically to 0. And so it would be nice to have some way where finding this threshold for the score that you actually want to use in the end is included in the metric.
Yeah, no, I completely agree that in reality there are a whole bunch of issues that arise. I guess my perspective is that like integrating developments and improvements over the long arc of time, ultimately the way that you get to 100% AP is by making both precision and recall 100%. So if we're generally pushing in that direction, we're generally pushing detectors to having better operating points for any level of recall. So I think in the long run, we're doing the right thing. At any point in time, it's questionable about whether any particular movement is like actually going to improve a detector. Yeah, but valuable comments. Thank you.
Yeah, thanks for answering the questions.
Yeah. Okay, so, all right, I've managed to put us 2 minutes behind schedule. So let me jump in now to the part that I think many people have been waiting for, which is the announcement of the results. So let me share my screen. I gather that you can see this now, the slides. Okay. Okay, so first let's look at the submissions that we had by year, just to get some context. So in the first year of the challenge, 2019, we had 10 submissions. Last year we had 9, and this year we had a little fewer. We had 7 in total, and 1 that was withdrawn due to an issue with external data. So just a couple of notes about this. So one is that thinking about future challenges, if you're ever uncertain about a data usage question, please ask via the LVIS Google group as early as you can in order to avoid any surprises later. And then the other is just that because we changed the metrics as just discussed, this may have created some issues that potentially could have driven down participation a little bit this year. Okay, so this was reflected in a few logistical challenges. So the new metrics are computationally quite demanding, as I'm sure all of you who participated experienced. And in particular, this caused a bit of an overload to the eval AI server that was hosting the challenge. And I just want to note that even though some of the submissions were not evaluated automatically at the time of the deadline, we did, after the deadline passed, go through and ensure that every valid submission that was received before the deadline was properly evaluated and is reflected in the final leaderboard. Okay, so with that said, now let's get to the leaderboard. All right, so in 7th place, we have Team Copy Paste++. In 6th place, we have the one withdrawn entry. So you can see that that doesn't really change the ranking all that much. In 5th place, we have Team Person. In 4th place, we have Team Pangu. In 3rd place, we have Team BUPT Priv ICA. In 2nd place, we have Team SSSSS. And in 1st place, we have Team FuXi-Fresher. Okay, so congratulations to everyone who participated. And these are really quite amazing set of results. And in particular, congratulations to Team FuXi-Fresher. So this is Wei Fu, Kongchang Ni, Ting Sun, Jun Liu, Yong Liu from the Tencent U2 lab. And they achieved first rank for the overall AP, but also very notably had an AP rare that was very, very close to AP common and AP frequent. And so I'd like to kind of put this in the context of the last year. And so first of all, there's a caveat that we changed the metrics. So it's not exactly comparable from year to year. And in general, because of the more stringent boundary AP, the results generally should be a little bit kind of skewed lower, not taking into consideration the improvements that were made. But I still think that we can look at some quantities like ratios, which may not be impacted very much by the change. And what we see is that last year, the ratio of AP rare to overall AP was about 77%, which was already a huge improvement over the year before that. And this year, it's jumped up to 99%, which is kind of remarkable. Now, this might make it seem like perhaps the rare problem detection, the rare category detection problem in LVIS is somewhat solved. I don't think that that's quite the case because there's still this issue that's not particularly well understood. It's really not understood at all, which is that AP rare seems to be somewhat inflated relative to AP common and frequent. If this is a topic you're interested in researching, please reach out to me to discuss it, because still haven't quite found a satisfying explanation for why this is happening. Okay, so just to kind of give a preview of the schedule for the rest of the workshop today. So we will have an analysis of results coming up next that go into much more detail than I just did. Then we'll have a talk by the BUPT Priv ICA team from third place. And then after that, coffee break. And then we'll have a talk from the second place team, team SSSSS. And then we'll have our second keynote from Professor Linda Smith of Indiana University. And then we'll have the final two talks before the panel. The first will be an invited research talk, and then a talk from team FuXi-Fresher, who placed first. And that will be a recorded video because they weren't able to attend in person. Okay, so with that, I would like to hand it over to Daniel Bolya, who will give a much more in-depth presentation and analysis of the results.
Thanks, Russ. Let me share my screen here. All right, can everyone see the screen?
Yes, looks good.
All right, so hi, I'm Daniel. I'm from Georgia Tech. I'm a PhD student studying under Judy Hoffman. And I want to, first of all, thank Ross and the team for inviting us this year. Today, I'll be going over some an error analysis I've done on the submissions using the TIDE error detection toolkit. So if you haven't heard about TIDE, it's an object detection and instance segmentation analysis toolkit where the primary goal is to break down each error in terms of its effect on overall AP. So one of the driving principles behind TIDE was to carefully design it such that it doesn't overrepresent different errors. You might be familiar with the COCO eval toolkit, which also does something similar in that it breaks down errors in terms of their change in AP. But we found in the paper, and you can read it if you're interested, that this actually way overrepresents some errors more than others. And so in TIDE, we sort of dealt with that issue. All right, then, so as a little bit of background, how do we compute errors in TIDE? First, we compute the regular AP of the model, and then we fix some of the errors in the model. And then we ask the question, how much AP do we gain? And finally, the error is defined as this improved AP by fixing those errors minus the original base AP. Now, one caveat to errors in TIDE is that the errors don't sum to 1. So in COCO eval and in potentially other toolkits, if you add your base AP plus all the errors up, you get 100 AP. So it sort of tries to fully explain you know, the lost AP. But we found actually AP computation is kind of not linear. So if you fix these errors, you don't get, if you reorder the way you fix these errors, you can change the magnitude of each errors and how they're computed. So actually this situation where you add all the errors up plus the original AP to get 100 actually completely overrepresents some errors more than others. So in TIDE, the numbers don't add up to 100, but for convenience, we put everything in a pie chart where it's all normalized. So what general errors does TIDE predict? Well, there you have the standard fare like misclassification and mislocalization. Those are probably as you would expect. Then there's also a bin for if an instance is misclassified and mislocalized simultaneously. And then, of course, we have the self-explanatory duplicate detections and background, which is if you have a false positive where there's no ground truth around it, so there's no potential for mislocalization or misclassification. And then just standard missed ground truth, so you didn't include this ground truth, or you didn't match this ground truth at all. And we also have aggregate metrics for all false positives and all false negatives as extra errors. And so, as Ross said, here are the results, and here's the results with the TIDE analysis. Now, I put this table up here not so that you can absorb this information. It's a lot of numbers. What I want to point out is that I've bolded each column, the best method in each column, and actually there's no one method. FuXi doesn't sweep the errors across the board. So some methods are better than others in different sort of error types, and That's interesting because it means that potentially, if you combine the features of these different methods, you might be able to create a better model in the end. All right, then to start out, I'm going to be doing some meta-analysis on the recently introduced boundary IOU and fixed AP that we just talked about. Specifically, to recall, boundary IOU was just a stricter IOU metric that used the boundary instead of the whole mask, and while fixed AP is allowing 10,000 detections per class rather than 300 per image. And so first and foremost, as expected, here I'm plotting localization error before using boundary MEP and afterward, and across the board for each method, boundary IOU slightly increases the localization error. Now this affects some methods more than others, and usually this is down to how involved were their mask prediction and refinement step. So how much effort did they spend in producing high quality masks? Then next up, and probably less surprising, more surprising, is fixed AP and its effect on errors. So first of all, as expected, the total amount of false negative error goes down from using fixed AP across all different methods. So except for methods that don't sort of exploit the fixed AP allowance, like person there didn't exploit that. But for the rest of the methods, the false negative errors go down considerably. And of course, this is expected because now if you're allowing more detections per image, which is in effect what this is doing, you now have matched more ground truth that weren't matched to before. But what's a little bit less expected is its effect on classification error. So actually, most of the decrease in false negatives come from a decrease in classification error. And that is slightly unexpected. You expect this issue to be in the missed ground truth. But actually what happens is, as Achal pointed out before, and Patrick also mentioned, these detectors are producing many object annotations for the same object with different classes because AP is sort of computed per class. And in a weird quirk in the LVIS evaluation, this is a federated data set, we don't know whether classes are guaranteed to be in the image for most classes. So for instance, if you had an airplane and your detector has mislabeled it as a bird, then if LVIS doesn't know whether or not there is a bird in the image, so it's not in the positive classes or not in the negative classes, then LVIS will not mark that as an error. You won't get a misclassification error in LVIS. TIDE still profiles that error because indeed that was a misclassification. And when you increase the number of detections your model is allowed to output, somewhere down the road, your model might output an airplane detection that is right on top of that original misclassified bird detection. And now LVIS will be happy because it got an airplane detection, and TIDE will also be happy because now you don't have a misclassification, and the bird detection goes back to being ignored. So one thing to point out is TIDE is specific to the metrics being used. So TIDE tells you how to increase on those metrics, not necessarily how to create like an overall better, more nice object detector. But so from the classification errors compared to last year are quite a bit lower because of this shift to fixed AP, and also some improvements in the methods themselves. And so now I'll be discussing some themes of different methods when compared across them. And the first of all is, again, classification. Classification was a big thing this year, even with the decrease in sort of classification error from using fixed AP. There was also a big improvement from using SWIN, a large visual image transformer, and ImageNet 22K pre-training. So the base classification performance of SWIN and ImageNet 22K is incredibly strong, and ImageNet 22K was allowed this year. Previously, we were only allowed ImageNet 1K, and this has sort of tremendously decreased the classification error even further for all the top methods that use it. And now, actually, interestingly enough, the top methods have less classification error than localization error with the way LVIS is computed. So here are the sort of error distributions for these 4 top methods that use SWIN plus ImageNet 22K. And you can see that for pretty much all the methods, classification is lower or equal to the localization error, which is very surprising. I'm going to put up on the screen mask CNN from the start of LVIS. So this is the sort of baseline, where classification is predominantly the most predominant factor in why mask CNN doesn't do as well. And now we're at a point where this classification score, both because of allowances for using ImageNet 22K, both because of architectural improvements and because of now this fixed AP metric, that now classification is not as big of a deal as localization. So how do these methods actually improve the localization scores? Well, FuXi and Bucht, for example, are very similar in their methodology, but differ in the way they refine masks. And that imposes actually a big difference on the localization error. So there's 2 actual ways you could make better masks. And one way is sort of the obvious way of creating better quality masks from the get-go. SSSSS does this and FuXi does this, where they use methods that increase the mask quality directly to get better quality masks. But there's also, with AP, there's another option, and that is rescoring the masks based on their quality. So AP is very sensitive to the scores that your detector outputs, and Bucht actually uses a quality aware module to rescore based on mask quality, which is interesting in that Bucht gets lower localization error than FuXi, even though FuXi has better performance overall. So it's an interesting strategic difference. Of course, Bucht's quality aware module also affects the masks because they do train on it. But the point is that rescoring is, so it's still a really important fact. Maybe rescoring based on so class with fixed AP isn't an issue anymore. But now it's good. But it's still the fact that rescoring based on IOU quality is really important. And there's no reason why these 2 sort of approaches couldn't be just combined. So that's also interesting to note. All right, then next up is sort of aggressive augmentation that all these methods have used. And here the top 4 methods all use some sort of copy paste plus some other augmentation, except for Bucht, which doesn't use any augmentation or any additional augmentation rather than normal ones. And we can see that this really affects their background error. So false positives that don't align with any ground truth. And of course, I'm not saying that so augmentation is the sole reason why Bucht has higher background error, but it is interesting to note that the copy paste and mosaic is a clear winner and a clear favorite among the top contestants, and it seems to really reduce background error by quite a bit. All right, and next up, as Ross said, well, first of all, the sort of distinction between LVIS and other data sets is its premier feature of a long tail. And that's why always we've had this large gap between APR and APF, even though, as Ross said, the APR is slightly overvalued, slightly overestimated. But now FuXi actually gets APR close to APF, as Ross pointed out. So that's very interesting and sort of a paradigm shift from previous previous years. And the technique they use, and you'll hear more about this in their talk, is just simple early stopping. And actually, as you continue training, the rare classes get worse, and so early stopping helps fix the error for them. And most improvement that I found using the tight error analysis, and this isn't completely conclusive, I think there needs to be more introspection done, but most improvements seem to be in terms of background error. So fewer false positive detections that are spurious. But there's a caveat which, even though the actual AP numbers are similar now, there's still a different distribution of error within each different category. So here at the left, I've sort of put the relative errors for each individual class frequency type. And you can see that the frequent and common classes have very similar error distributions, and most in FuXi, most are based on localization, whereas for the rare classes, most of the error still comes from classification. So it's not to the point where we can classify AP, you classify rare classes as much as good as frequent classes, but it's still a much less of an effect than in previous years and for previous approaches. So classification is still a big piece of the pie, but it's not as much as it was before, and it's getting closer to localization. All right, and then some concluding remarks here. Some takeaways from this analysis is that new evaluation criteria makes classification itself easier. Now, this isn't really reflected in the overall AP because, again, so LVIS will discard misclassifications a lot of the time, and it makes localization harder. So overall, the APs are slightly lower. But the point is that the actual misclassification errors, just due to quirks in evaluation, are lower. And the best methods take advantage of sort of big transformers and ImageNet 22K to get record low classification error, which is also new for this year's challenge, and quite interesting that we're at this point. And methods that didn't use transformers and ImageNet 22K struggled in both localization and classification. This is kind of to be expected. I mean, it's always been the case that using bigger backbones gets you further. And one very interesting thing to note is that, for instance, FuXi doesn't have the lowest localization error. So there's still rooms for improvement in the best methods in terms of localization, maybe not as much as classification, but still primarily in localization. Custom data augmentation strategies do work. So some of the methods listed use some custom data augmentations like Pangu, but copy paste plus mosaic, a pretty off-the-shelf recent state-of-the-art data augmentation method, is very strong on its own and probably strong enough. And finally, classification still remains the most difficult part of detecting on rare classes, but it's not nearly to the extent it was before, due to using ImageNet 22K and also the fixed AP. That's more of a evaluation change. All right, thanks for listening. The features that I've implemented for this workshop will be made available in TIDE version 1.1 soon. TIDE is available at that link. And I guess I'm out of time. If you have any questions, you can probably just leave it in the chat.
Thank you so much, Daniel. That was a super interesting presentation. I think that the thing that I was maybe relieved to see a little bit in there is that when you did the analysis for breaking it down into rare, frequent, and common categories, that there still was a big classification performance gap on the rare categories. That makes me think that there's still a bit of a challenge to be solved there. Okay, so it looks like we're still right on schedule. And so I would now like to invite the third place team to give their presentation. So this is team BUPT Priv ICA, and the presentation I believe will be given by Lu Yang. So if you're here, please feel free to share your screen and start your presentation. See, I think I saw Lou in the participant list until just a second ago, and then they dropped away. So hopefully that's just a disconnect and reconnecting now.
Hello?
Hi.
Oh,
Yeah, we can
hi.
hear you now.
Very sorry, I just restart the Zoom.
Yeah, no worries.
Okay. Okay. Hello, everyone. It's an honor to be here to introduce our method we use in LVIS Challenge 2021. LVIS is a large long-tailed instance segmentation dataset with 1,203 categories. With this long-tail distribution, traditional object detectors have proven to be ineffective. In addition, as a federal dataset, LVIS adopts an non-exhaustive annotation strategy for some categories. Moreover, compared with Coco, LVIS has the more fine-grained high-quality mask annotation, including more detailed masks and more accurate edges. Towards LVIS fine-grained high-quality mask annotation, we adopt GCE head and QAM. The former allows a better focus on detailed information and refines mask results, and the latter pays much attention to the mask quality estimation. For GCE head, because the scale of different instances varies greatly, which requires the feature maps to capture multi-scale information. The ablation experiment of GCE head is shown. Spontaneity with GCE head achieves a very competitive result. On this basis, GCE head can improve 1.1 of mask AP and 1.6 of boundary AP. The quality estimation is an important issue. Inaccurate scoring or ranking the network output results in a large number of low score with high quality or high score with low quality masks. To obtain good sorting results of high quality masks, we use quality aware module, which fuses the different quality information to estimate the output quality. As shown in the table, QAM can improve another 1.1 mask AP and 0.9 boundary AP. It can be seen from the picture that QAM can lead to a better mask with improving the ranking strategy of the network output. With mask arson as our baseline, we get 16.1 box AP and 15.7 mask AP. To address the LVIS long-tail distribution, repeat factor sampling is adopted. In addition to the federal annotation, we adopt federal laws according to the experimental results. By using RFS and federal laws with CenterNet2, max AP improves from 15.7 to 25.7. To obtain high quality instance segmentation, we adopt Spontaneity, GCE head, and QAM mentioned earlier. With the box AP up to 36, mask AP up to 35.2, and boundary AP up to 31.4. In order to enhance the feature extraction capability, we replace the backbone with transformer swing large, which serves as a general purpose backbone for computer vision. Through swing large pre-trained with IMNet 22K, we increase 10.3 of box AP, 8.1 of mask AP, and 8 of boundary AP. We consider that IMNet 22K includes almost all categories of LVIS. The LVIS categories can be better studied through the pre-learn. We follow the SWA method to train our detector for an extra 10 epochs using cyclical learning rates, and then average these 10 checkpoints as our final model. With SWA, we gain 2.3 improvements in boundary AP. We consider that the long tail distribution makes the model parameter space more uneven, which is worth of first study. Through longer training, mask trick, and SWA, the box AP can up to 49.2, max AP can up to 46.2, and the boundary AP can up to 42.9. We design a detection selection method and adopt multi-scale testing in our test time augmentation. According to the study in the fixed AP, we should ensure that the number of detections in each category reaches 10,000 in order to improve performance. So we select detections according to the following constraints. First, we set the scarce threshold to 0.01 and remove the limit on the number of detections per image. To ensure that the number of detections for each category is not less than 10,000, we force the top scoring detection of each category to be retained. For categories that already have more than 10,000 detections, this move will have no impact. Finally, the results for the entire 20,000 images evaluation site are ranked with each category, and the top 10,000 detections for each category are taken as the final results. For multi-scale testing, first we need to choose the right scale. Too much scale is a lot of testing time while not necessarily achieving the better field result. On the wheel side, we perform box detection on a range of scales. By comparing AP small, AP medium, and AP large, we selected a series of scales taken from 600 to 1,200 pixels. On each scale, we use flip test. Secondly, we make the box AP of each scale as weights and use weighted box fusion to fuse all boxes to get the final boxes. The weights on the test challenge set are the same as the validation set. Compared with NMS, WBS achieves 0.9 improvements. Then we use the box final to replace the proposal generated by the detector to get a higher quality ROI feature. Finally, we fuse the three scale masks as our final result. With our test time augmentation strategy, we achieve 52.3 box AP, 49.4 mask AP, and 46 boundary AP on the well side. On the visualization of the well side, the prediction results have a very fine mask and boundaries. That's all, thank you.
Right, thank you very much, Lou, for the presentation. So we do have time before the coffee break for a couple of questions. If there are any questions from the audience members, feel free to unmute and directly ask them or ask them in chat. In the meantime, while people think about that, I'll ask a question or two. So is it correct that in your method, you didn't make any use of extra data augmentation techniques during training, like a copy paste or mosaic?
Yeah, we don't use the copy paste or mosaic training data augmentation because we thought we consider that actually it's hard to implement on our framework.
Yeah, I understand.
Yeah.
Yeah, and then so I guess that maybe one of the most interesting things here is the enormous improvement that's brought about by using the SWIN transformer large. And I guess that there are kind of two orthogonal components that it would be really nice to disentangle. So one is the change of the network architecture, and the other is the change of the pre-training data from ImageNet 1K to ImageNet 22K. I mean, they weren't in this wasn't in your presentation, but I'm curious if you have any additional insight into how those two factors influence the overall performance.
Yeah, we on the former of the challenge, we only use the swing base, which is only pre-trained on the ImageNet 1K. But after the September 1st, we saw the rule changes. So we use the swing large with the ImageNet 22K. But we also tried the C swing large, but it's very difficult to train the C swing large backbone in a short time. So we think the swing large is a very consensus backbone. The bigger scale datasets, pre-trained dataset is actually useful for the long tail distribution. So so we choose the swing large with the ImageNet 22K.
Okay, and do you happen to recall from the earlier experiments where you were using the SWIN base model trained on ImageNet 1K about how much of an improvement you were seeing from that?
Yes, we have the experiment results about the SWIN base with ImageNet 1K. Just about 41 points box AP. It's about 3 or 5 lower than the swing large.
Okay, all right, yeah, interesting. Thanks for sharing that. Yeah, so maybe if there's 1 or 2 questions from the audience, otherwise we can move to the coffee break. Okay, it seems like everyone's a little bit shy. That's okay. All right, so thanks again for the presentation, very interesting. So let me just share this slide so that anyone joining will see where we're at. And let's go ahead and take about a 15-minute coffee break and then reconvene at 10:15 Pacific time. And yeah, thank you very much, and looking forward to resuming and having an exciting second half of the workshop. Thanks. Okay, so the coffee break is just about to come to an end. And I would like to ask if Lin Song from team SSSSS is here to present.
Okay, I'm here.
Okay,
Is
great.
that cool?
So I've stopped sharing my screen, which should enable you to share yours.
Okay, thank you.
Great.
Okay.
Yeah, so whenever you're ready, feel free to take it away.
Okay. Hello, everyone. My name is Lin Song. I'm come from Xi'an Jiaotong University in China. Today, I will represent our team LVIS to give a report. sorry. Here is the outline. We give an statistical analysis to the LVIS dataset and found 3 critical challenges, including long-tail distribution, boundary quality, and small objects. To address these challenges, we propose a strong framework for instance segmentation and a new vision transformer backbone for 4K resolution images. The distribution of categories in LVIS dataset is extremely imbalanced. The LVIS dataset has about 300 tail classes, which has less than 10 instances per class. Many of them even has only 1 instance. To elevate this problem, some previous works based on loss function and classifier modification are proposed. They achieve a significant improvement in tail classes, but in this year, the metric for LVIS challenge has been changed to the AP fixed, which makes most of previous methods for long-tail detection only has minor improvement. Moreover, as shown in the table 3, the AP real is still inferior to the AP frequent by about 10 points. So the long-tail distribution is still a big challenge in this year. The second challenge is the new AP boundary metric. It focuses on the boundary quality by using the new boundary IOU. This new evaluation metric raises a big challenge for the instance segmentation, especially for the large size objects. As reported in table 3, the AP large is reduced by 22 points by using the new metric. Luckily, the higher resolution features or images can significantly improve the boundary quality. That could be a key factor to solve this problem. The third challenge is the imbalanced object size. As shown in the figure, the LVIS training dataset has about 64.4% small objects. That means the set length of most instances is below than 32. Similar with the boundary metric, we need higher resolution images to increase the recall rate for the small objects. To this end, we use ultra high definition images, the 4K images, to improve the recall rate of small objects and the boundary quality for the large objects. Specifically, we first build a strong baseline framework for instance segmentation. Then we propose a new backbone network based on a new effective vision transformer for 4K images, which enables better representation capability. Here is our strong baseline. We can divide the framework into 2 parts. The first part, training data augmentation. We use mosaic and copy-paste augmentation to increase the diversity of instances and background. The repeat factor sampling technique is also used for tail classes. Following the conventional settings, we use multi-scale training with maximum 1,400 shortest set length. Besides, about the architecture of the baseline, we adopt a REST-nest backbone with context modeling and deformable convolution networks. And enhanced HTC light has with deformed RY pooling is used for instance segmentation. To further improve the performance of tail classes, we use a simplified classifier calibration model based on our previous work in CVPR 2021. With these modifications, our method achieves 41.7% in AP seg, which is superior to the winner of the LVIS 2020 by 2.9%. Besides the framework, we mainly focus on the design of the backbones. Recently, Vision Transformer shows impressive performance in various vision tasks by using self-attention mechanism to model long-range dependence. However, The standard self-attention needs extremely huge computational and memory consumption, especially when handling large size images. It makes the standard vision transformer not available for 4K images on the GPU devices. Many efficient variants of VIT are proposed to reduce the complexity. For example, swing uses window attention and C-swing uses extra attention. However, the window attention in swing could not well capture the global context, and the C-swing will lose the local and textual details owing to the extra attention. Besides, the memory cost of the extra attention is still unacceptable when handling 4K images. To achieve a good balance among local details, global context, and efficiency, we propose a new 4K VIT backbone. It is made up of a dilated long-range attention and an adaptive precision short-range attention. The long-range attention uses dilated extra attention, which can significantly reduce the memory cost while maintaining the similar performance. In the short-range attention, for each query, we adaptively sample several pixels as the key value pairs and perform a sparse attention on them. We fuse long-range and short-range attentions as a single process, called it 4K VIT. For a file comparison, our 4K VIT follows the same settings from C-swing for architecture configuration and training schedule. The number of key value pairs in short-range attention is set to 7, 7, 21, 21 in different stages. Here is the result of our 4K VIT. Under the similar complexity, our model achieves the state-of-the-art performance on image classification, object detection, and instance segmentation. Specifically, in classification task, our 4K VIT achieves the 0.5 absolute gains over the C-swing. The performance gain is more significant in object detection tasks, where on the COCO dataset, our backbone achieves with the mask-RCN framework, our backbone achieves 50.2% in AP box. Moreover, we pre-trained the 4K VIT large, use ImageNight 22K for better representation capability. Without bells and whistles, our framework achieves a 45.2 AP boundary using single model and a single scale. It means our method has achieved 4.7% absolute gains over the strong CN backbone. Even compared with the swing larger backbone, our 4K VIT still has 4.5% ahead. Besides, the table 4 demonstrates high-resolution images is critical for high-quality instance segmentation, while 4K resolution can outperform the 2K resolution by about 1.7%. Like the previous methods, we further apply the multi-scale testing augmentation to our model, but unfortunately, we don't have enough time to explore a proper way for our model. We only achieve 0.3 absolute gains over the single scale model. It is quite a pity. But I believe our model can obtain a much higher performance by using a better augmentation procedure. To promote community development, we will make the code public. Thank you for listening.
Right, thank you, Lin, for the talk. Again, we'll have this format where participants in the workshop feel free to unmute and jump in and ask questions, or if you prefer, you can ask a question in the chat. So in the meantime, I'll ask kind of a similar question to the last presentation. So I'm curious for your 4K VIT large model. I saw that you were pre-training it on ImageNet 22K. I'm curious if you had tried training it on ImageNet 1K, and if so, what the results were.
Yeah. When we pre-trained our model with 1K ImageNet 1K, it can still has a 0.5 about 0.5 absolute gains over the C-swing, and a large margin to the swing. Yeah, if we pre-trained on the small backbone, because the larger backbone need more data to ensure the currents.
Mm-hmm. And did you try using the ImageNet 1K pre-trained model on LVIS? And if so, what was the gap compared to the ImageNet 22K model?
You mean directly training on the LVIS dataset?
No, I mean, so if you take your 4K VIT large and pre-train it on ImageNet 1K, and then use it in LVIS, how much worse is that compared to having done the pre-training on ImageNet 22K?
Okay. We just test our we just test our model, our small model on the LVIS. That is about 41.6 AP boundary. If we use the 4K VIT tiny.
Okay. Let's see, there's one question from an audience member. How long do you spend on training ImageNet 22K?
Oh, that is, we don't have enough time to train from the scratch. We fine-tune the weight from the C-swing weight. We just trained about 10 epochs.
I see, interesting. And then I guess I had one other question, which is for the short range sparse attention, is that using a technique that's similar to deformable attention? Is it the same as that, or is it a slightly different formulation?
Yeah, it is similar, but it is not identity. The deformable, the weight in the deformable attention is generated only by the query, but our weight is generated by the query and the key, by the distance between the query and the key.
Okay.
So it is not identity.
I see, thank you. Okay, it seems that maybe there are no other questions from the audience. So yeah, thank you again for your presentation.
Okay, thank you.
Okay, so next up, we're going to have our second keynote. And okay, great, I see that you're here. Okay, so it's my pleasure to introduce Dr. Linda Smith, the Chancellor's Professor in Psychological and Brain Sciences at Indiana University. So I've been following Professor Smith's work for a number of years now. In particular, I've been fascinated by her studies that characterize visual category learning in infants. And I think that is going to offer a fascinating perspective that challenges many of the central practices that we adopt in the computer vision community for trying to address our analogous problem of learning categories from few examples, such as the problem that's posed in the LVIS challenge. So I'm very excited to hear this talk, and it's my pleasure to welcome Dr. Linda Smith. And we're excited to hear about what you have to tell us about babies' bodies and learning to recognize objects. Oh, it looks like you're still muted. Hopefully you can unmute on your own.
I can unmute on my own. And
okay, great.
Now I can share on my own.
Hopefully, if not, we'll help you. Yes, we see it.
Okay, so here we are. There we go. All right. So as you may or may not know, I'm a developmental psychologist, and so I'm not an expert in your field, but I do think that I might have some insights you might find useful. So here's where I'm going to begin. Vision begins with 2D images projected to the eye or the camera. And these projected images vary continuously with every change in the spatial relation between the eye or the camera and the entities in the world, with changes in lighting, with changes in the spatial relations among the things in the world. And how those images vary, though, is not, it's pretty massive. They can vary a lot, but they are constrained by the geometry of the surfaces, by the physics of light, and by the medium, air, smoke, water, whatever, through which the light from the entities is reflected to the eye or to the camera. So these are the facts of vision, and they certainly hold for all moving agents in the world. I think they also have relevance to just thinking about recognizing objects and images as well. And you might see that as we go along. So what I'm going to suggest is that, okay, so vision has two sort of classic problems that people think about. One is object constancy, the fact that we as human perceivers at any rate perceive an individual object as a constant thing, as an individual thing, despite the inherent, continuous, and often considerable variation in the projected image from that object. The second big problem in vision that's also captured a lot of attention is visual object recognition, our ability to recognize never seen before things as members of categories, as dogs, cups, flowers, and so forth. So here is the big idea that I want to propose, that the learning and processes that underlie object constancy, seeing an individual object as the same thing, despite the variation in the projected images, is in fact the basis of human prowess in visual object recognition, and more specifically in the ability to rapidly generalize categories to never seen before instances from perceptual experience with a single instance. So here's what I'm going to talk about today. These ideas emerged from my long work on how it is that babies learn to recognize the common objects of their everyday life. I'm first going to talk about the developmental trajectory. This is old work and pretty well established, so I'm going to try to go through it fast. Then I'm going to talk about the natural statistics of toddlers, infants and toddlers' object experiences, which I think are deeply informative to the answer to this question. And then I'm going to offer my theoretical proposal. So the developmental trajectory. The phenomenon I'm going to concentrate is what's known as the shape bias in early object name learning. This is something that anyone who has a toddler knows is true. The toddler sees for the first time, let's say, a John Deere tractor working in the field, and they just happen to have never seen a tractor before. Maybe they live in Brooklyn. And this, they see this tractor, they watch it work in the field. Dad says, tractor, 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 tractor. Okay. They watch it, they're really interested, fascinating. From that day forward, that toddler is likely to recognize all variety of tractors, Massey Ferguson's, antique tractors, toy tractors, tractors in books, but they won't include the backhoe or the dump truck or the mail truck. They actually form from one experience of a single object, the category tractor. Children robustly do this. Typically developing children, starting at about age 2.5, although it develops incrementally, so you see early signs of it before that, but they're really robust at it by 2.5. The original paper demonstrating the shape bias was reported in 1988. There are, if you go to Google Scholar, well over, probably more than this, I couldn't do an exhaustive search, 5,000 papers. And they cover the role of the shape bias in typical development for object name learning and its relation to visual object recognition, atypical development, in many forms of atypical development, autism, language delay, some other domains, a shape bias is never demonstrated, or it's very, very late. And some people have become interested in machine learning. There's just a smattering of references here. All right, so how does this happen? Okay. Well, the classic view of object recognition and object detection and segmentation and all the fundamental abilities was that it was principally about object shape. I've listed a few of the names of some of the older giants in the field who have said so, okay? Now this makes sense if you think about the problem of object constancy, how images can vary, how the image itself can vary with the way the light is reflected from the object depends on the geometry of surfaces. That's basically shape. But the problem is, oops. Yeah, there we go. All right. So if you look, the problem is that shape is not a trivially easy thing to characterize. What do we mean by being the same shape? If you ask adults, they will say chairs are chair-shaped. That's how they know what a chair is. They're chair-shaped. But all the varieties of chairs and their various poses are only the same shape under some right description of object shape. But it's also the case that recognizing an individual object is the same thing. Object constancy is only going to happen with some right description also of object shape. All right, so what do we know about the early development of shape perception? Okay, well, the evidence suggests that there is a shift from piecemeal category-specific features as the basis for object recognition to the three-dimensional geometry of shape itself. So early on, 1-year-olds, 6-month-olds, 12-month-olds, they tend to recognize objects by category-specific features, okay? So it's a duck if it's got a duck bill, okay? It is an ice cream cone if it's got ice cream on the top. It is a cat if it's got whiskers and cat ears, okay? And pretty much nothing else varies. And so little children, young learners, 18-month-olds, can typically do the things that I have put little check marks by. If you put them in image recognition tasks, they can recognize a duck as long as there's a duck bill, but they are really not good, okay, at recognizing it from kind of caricatures of the shape when there's major occlusions or when it's in massive colors. 6 months later, your typically developing child can do all of this, okay? And they can recognize objects which an 18-month-old can't. An 18-month-old, if I were to give them those three-dimensional gray things down the bottom and ask them to take, they're three-dimensional, and real holdable things, and I ask them to give me the ice cream cone, they can't do it, okay? They don't have quite the right parts and quite the relational structure, okay? They can do it if you ask them to give you a ice cream cone with a rich everyday object with all the category specific features, but they can't do it with these 3D representations in terms of the major volumes and their spatial relations to each other. Okay. All right. All right, I'm frozen in some way. All right, let's try this again. Oh, there we go. So the shape bias in object name generalization develops over the same developmental period that recognizing objects by shape develops. So your typical shape bias task looks like, and this is what was done in 1988, looks like this. A child is given some three-dimensional object they can move. They're getting a lot of varied input in terms of the projected image from this object. They can move, they can hold the object. And you say, this is a DAX. Then you give them two other three-dimensional objects with one that is roughly similar in shape in an abstract way and the other, which is not, okay? And you ask them which one is a DAX. And they choose the object that is similar in shape. People have done this with more complicated real-world objects as well, okay? And the shape bias, as I said, just gazillions of studies on, highly robust phenomenon. The all these changes are deeply related within individual children between 1 to 2.5 years of age. Their ability to recognize their perception of the shapes of everyday objects, to recognize objects in terms of the volumes, the relational structure of the volumes that comprise them, the immediate category generalization of shape of a novel object like a DAX, and with their growth in object name vocabulary. All right. So that's what we know about the developmental trend toward one-shot learning and generalization of individual categories in children. All right. So in children, one-shot learning is related to developmental changes in object recognition by visual shape and to learning object names. It develops incrementally. By 2.5 years of age, in typically developing children, it is quite robust, okay? So what the question is, what is the developmental mechanism? And this question has led me to what I have been doing for the last 10 years or so, trying to figure out what the developmental mechanism might be by looking at the natural statistics of children's visual object experiences. Now, most people, when they say want to understand what the learning mechanism is they construct some theory or they architecture or they test specific hypothesized mechanisms. But it seems to me the best place to figure out the way or what the mechanism might be is to actually look at the training data, the natural training data, because that defines what the task it is that these children have to solve, and it contains the knowledge to be learned. And if you are going to have some kind of learning machinery that can do this as rapidly and robustly as young children, then you're going to have some learning machinery that matches the task to be solved. So what I have been doing for some time now is trying to capture what the images are that are projected to baby heads and eyes as they go about their everyday business. We use both head-mounted eye trackers and head cameras. And we have done this work in a series of increasing control on one side to increasing naturalist on another. In some experiments, we bring babies into the lab. It's high resolution and it's naturalistic free-flowing play, but everybody's wired up. So maybe it's not completely naturalistic because we have head-mounted eye trackers, motion sensors, variety of things. Then we have the medium one, which is a toy room where children typically just have head-mounted eye trackers on, free-flowing play, cluttered in the lab. And then the data that I'm mostly going to talk about today, which is home view, and we have a parallel data set from India, where we give head cameras to parents and they put them on their children, and we either ask for day-long recordings or we sometimes ask for recordings of particular events across multiple days, like mealtime or play. All right, so I'm talking about the home view data set. For the most part, these are 101 infants in the US, 3 weeks to 24 months, 4 to 7 hours of head camera video from each child. We have over 800 hours of video. Parents are told in these studies, going the wrong way. We're told in these studies that we were interested in vision, not that we're interested in anything else, any kind of vision, and all awake visual experience was of interest to us. All right, so I'm not going to take any time on this because I don't want to. Head cameras measure, but I'll just say this, assert it, and you can believe me. Head cameras measure what's in front of the head, okay? They do not measure where the gaze is inside that image. However, human beings from babyhood to adulthood primarily look to the center of an image, okay? You may notice something in the periphery, but if you're going to look at it for any sustained time, you go to the center, okay? So the images themselves, the head camera images or scene images, provide a really good basis for estimating the input available. All right, so what I want to talk about today is object categories in the everyday lives of toddlers during that period, starting at about 12 months, when there are all these changes in object recognition that seem to be related to rapid learning and generalization of new categories. And the work I'm going to talk about is Elizabeth Glerkin's dissertation just defended recently. And what we have done in this work, have 3 papers, is look at the meal times of infants collected at home from the head camera. And we have 350 mealtime events. These are all children older than 12 months of age, but younger than 2, who involving any kind of, we define them as events that are involving any kind of food or dishes or eating. And we sample these 350 events at 1/5 hertz every 5 seconds, giving us about 18,000 images in the corpus that I'm going to talk about. The first thing is when you look at all these images of meal times, what you find is that there are many, many different categories of objects there. We have people seen to text, recognize all the, try to list all the objects that are in each image. And there's lots of them. About 1,000 different kinds of objects are recognized often enough to get put on a graph. However, what you find is some categories are pervasively frequent and most others are extraordinarily rare, okay? In a corpus of 18,000 images occurring once, twice, 5 times. So there's a very few categories, okay, that are pervasive. And there's a long tail of things that are almost not there at all. The very pervasive categories, those that are highly, highly frequent, okay, so this is a proportion of frames in the rank order of individual categories shown in the figure. The highly frequent categories are also categories that are typically named by nouns that are normatively among the first nouns that infants learn. Cup, spoon, bottle, banana. So just one fact of what the data looks like, there are very few categories are represented pervasively, okay? And they are there across all these different toddlers in the US, and they're there at a lot of meal times, a lot of images, okay? But I want you to keep in mind, this is relevant to what you all care about, that long tail of these less frequent things, by the time these infants are 2.5 years of age, they're going to be able to recognize examples of these rarer categories, the long tail, and to rapidly learn brand new categories that they haven't seen before, like artichoke. But it's not just the case that there is an extremely skewed distribution of the categories available at meal times, but that the unique instances within these categories are also extremely skewed. So this is just a small sampling of images of sippy cups from a child who contributed 7 hours to the corpus. And in 50% of that child's images, this one sippy cup was present, okay? So not only are there relatively few categories, but there are very few unique instances present for each of these highly frequent categories. And what we did was a detailed, actually, analysis of the 10 most prevalent categories in the mealtime corpus. Each of the categories selected was experienced over multiple days of meal times by multiple children. And we determined for each child who contributed data, the frequency of each unique identity, okay? And what I want you to see here is these aren't like odd things, like just my own sippy cup or my own favorite teddy bear, okay? The plates that a baby sees, okay, over 4 to 5 meal times are principally just one plate, okay? The spoons that the child sees over 3 to 5 meal times, okay, are principally just one unique spoon. The tables, okay, the windows, okay, one individual window, one individual table. Now you may be thinking to yourself, oh, no, I'm just going to show one thing. So before I go to that point, now because children contributed different amounts of data, and you may be thinking to yourself, if you just kept moving on and giving the kid more and more days, we just kept going for a month or so, surely the number of unique instances that the child has experienced would increase. It wouldn't always be like just the same table or the same plate, okay? So as a first way to kind of look at that, what we've done here is for each individual child, those are the different colored dots who contributed to the corpus, we're looking at the cumulative frequency across segments of frame, and each segment was defined as 250 seconds. So it's sampled at 1/5 hertz, okay? And what you can see for the individual child is a cumulative count of images that contain the category, in this case, spoon et al, okay? And as you go more and more and more segments, of course, they see more and more images with spoons in them. But if you count the number of unique types of images they've seen, that's on the second half of this graph, you can see that it's absolutely flat, okay? The number of types is not increasing no matter how much more time we give this child. All right. Now you may be saying, why so selective? What are these people doing wrong? This just can't be the case. There's loads of spoons and houses and loads of cups. Well, the reason why it's so selective are the constraints of space and time, okay? We have done similar sorts of things with adults, and I'm going to tell you that if I put a head camera on you, there would be likely 1 coffee cup, maybe 3, that would dominate all your experiences of coffee cups. Where you spend most of your time, let's say, sitting at your computer, the window in that room, if you're lucky enough to have one, that would be the window that would pervasively, in terms of the amount of visual experience, dominate, okay? This is just space and time. You're in a place, you spend time in that place, you see what's in that place, and it's going to give you an extremely skewed distribution of amount of visual experience with individual objects. So what we've got is that the day in and day out experience with individual objects, your own personal sippy cup, and your day in and your day out experience with few categories, cups, spoons, bowls, dogs, shoes, okay? Somehow this input gives rise to the ability to hear a name and know to generalize it by shape, and it doesn't have to be exact shape either. It gives you the ability to recognize objects from very abstract kind of shape information about the relational structure of major part, and it gives you the ability to become a one-shot learner of real-world categories. Okay. So how does this work? Well, one question to ask is, what's the teaching signal? And a certainly reasonable hypothesis is that it might be in terms of labels. After all, these increases in object recognition coincide with increases in object name learning. We don't know, one could be cause, one could be consequence. We don't know that, but certainly you might think labels were doing some work. But the next thing I need to tell you about the input or the natural statistics of babies' worlds is that herd names for objects are incredibly sparse. So to look at this is again the mealtime corpus. We selected categories to study more deeply in terms of their input in the corpus by choosing only categories that are normatively learned, early learned object names and object categories, so that they would be in your typical child's productive vocabulary by 18 months. And then we took the 25 most visually frequent categories, did that independently. And then independently, we selected the 25 most lexically frequent, that is, somebody named these objects in the child's hearing, categories, independently done. And you can see right from my little Venn diagram here that the 25 most frequent visual categories overlap a little, but not a lot, with the 25 most frequently named categories. Okay. And these are mostly food items or table items or things that are around tables for children. Okay. So we looked at a number of metrics across this, and I want to do this reasonably fast here. But so some of these objects, these are real people's meal times, and some of these objects are very prevalent in the meal times and some are not, and that could just be due to our sampling. and the age of the babies. For example, pizza's not typically in 12 to 13, 14-month-olds, just beginning in their diet. So even though pizza showed up, it's not super frequent. If we were doing 2.5-year-olds, it'd be very frequent, okay? So here I'm just showing the meal times in view for each of the categories we're looking at, the meal times they were named, but what I want you to see is both for the pervasively present object categories and of the top 25, of the ones of the categories that were selected, even the less frequent ones, they're all much more visually present than they are named overall. And it is very, very rare for any of these items to be both in view and named, okay? And this is true, whoops, go back. This is true when you look at the top 10 objects visually present and the top 10 objects that are named by parents, okay? Visual presence is much, much greater than naming. And there's just not very many cases where the objects are being named, okay, where they're both present and being named. Those are just rare, okay. So we have pervasive visual experiences with objects and rarer naming. And on the bottom here, I'm showing you how these emerge in time. So each one of those lines is a single meal time. And what we've done here is across all the children in the corpus, we have simulated what 200 meal times would like, sampling from the data in the corpus of cases where the object was present, the name was present, and the object and name were present. And what you can see is the experience over 200 meal times with these statistics would be one in which there's a lot of visual experience, an occasional visual plus naming, those are the green lines. Naming without the object almost never occurs, but it does occur a little bit, okay? So you have all, so what is it like? You have mealtime after mealtime after mealtime with the table in front of you. And then every once in a while, I don't know, every 10 meal times or so, a parent may name it. Same with your sippy cup, same with your plate, same with the spoon. Okay. So the point I want to make, I want to just go back and say what I think. The whole point of just saying to you this is I'm pretty sure that names are probably contributing to the baby's learning about categories and visual recognition, but it cannot be the driver, okay? The visual experiences are far more pervasive, and it rather seems just by looking at this more likely that the visual experiences are providing the foundation for learning the labels than that the labels are providing the foundation for learning the visual categories. So another possibility is that the child's own behavior is both the data generator by what they choose to look at, by where they move, by what they hold, both generating the data and is perhaps the source of a teaching signal. So the way we've been thinking about this is when you look at what's happening in these head camera videos, for toddlers this age, during this period, their hands are on objects all the time. Okay? And if you look at the data, it has a kind of structure that's illustrated down below, where what they do is they seem to pick up an object, play with it for a period of time, generating visual data about it, a lot of different projected images from that object, put the object down, then they pick up another object, they play with it. Someone may come in and name it, maybe, maybe not. Put that object down, may go back to the original object they were playing with, play with it, put it down, okay? And in collaborations with Jim Ray, we have been looking at what kind of learning might emerge from this. And I'm not gonna talk about that because you guys are the experts, not me. All right, but what I do wanna do is think about how this might be the fact that the babies are the self-generators of these data, and how that might play a role in the learning mechanism. I just want to set the stage for that idea. But I'm going to begin not talking about what babies do with their hands or bodies first, but about the visual properties that we know are associated with toddlers' learning of object names. So these are experiments with 18-month-olds. And what we did was we brought babies and their parents into the lab to play with toys that we made up, never been seen before. And we taught the parents the name ahead of them. So what happens is the parent and the baby play with the objects. for a period of time, 6 objects, 6 different names. And at the end of the play period, we test the baby, say the name and see whether the baby will retrieve or look at the object that was named. And we have replicated this result 3 times. So what we do after that is we, so they played with the object, we're recording the field of view images from the head camera for the baby, scene camera from the baby. Then after we've tested them, we determine which object names the baby has learned and not learned. And then we go back in and look at the visual properties of the objects whose names the baby has learned versus the visual properties of the objects whose names the baby did not learn. And babies this age playing with 6 toys with 6 novel names, they only learn on average 2 to 4 names max, okay? They're young. All right, so what are the visual properties? So what I'm showing here is on the x-axis is time. The little blurry utterance signal here is when the parent named the object. Then we're going to look at visual properties for 10 seconds before and for 10 seconds after, very long time. And we're going to look at them for object names that were learned by the baby when tested and for object names that were not learned by the baby at tested. And going to look at the visual properties of the visual size of the object in the image and its centering in the image. And what you want to see is that for the learned object names, they are much bigger in the image than are the competitors, that is the other objects in the child's view, when the object is named and for a long period. That's about a 7-second difference here. For a long period, both before and after the object was named. And when the object names were not learned, these differences were not quite there. And similarly, they are more centered. This is sort of upside down for thinking about center. This is closer to the center. So the named objects, when they're learned, are much closer to the center of the child's visual field than, and more distant in the image from the competitors when the object name is learned than when they are not learned, okay? All right, I began with that because it is the way the body of the toddler and the toddler's behavior is what creates these visual data, okay? So we've done a lot of work on what the baby's doing when they learn object names in this kind of a context. First of all, they're much more likely to learn object names when the head is stable than when it's not stable. They're much more likely to learn object names when they are holding the object than even when their parent is holding the object and making a really good big image of that object. Why is that the case? Because holding an object, okay, stabilizes the head, okay? It centers the object in the visual field, and it puts all the contrast, the high contrast, the highly visible visual information in the center of the visual field. Okay? So babies holding objects at midline creates really good conditions. Stable head, so you can maintain the difference between them and the competitors over time, and high contrast. Better visual conditions. It also creates dynamic input, okay? When babies are holding these objects, they're not looking at pictures, okay? But when they or their parents are holding their objects, you are having a variety of images of the same object, okay? So here's this little thing here being picked up by the parent. These are all the cases where the parent actually named it. A lot of images of that one object in that period of time, okay? So we've done a lot of work also looking at what the images look like in this part of, when the children are holding them and visually examining them. And what we have found is that their input is biased and highly structured, okay? They're not looking at a still object, they're moving those objects. They both move their head around them and they move them with their hands. So here's how the objects are biased. But infants, these are 1-year-old, 1.5-year-olds, 2.5-year-olds are biased to look at objects in which the major axis, either the axis of symmetry or the axis of elongation, is parallel or perpendicular to the line of sight. Those are these images. These are all what are called planar views in vision research. So they're parallel or perpendicular to the major axis to the line of sight. This is just when they're held upside right, and when they're held upside down, 1-year-olds don't care about holding them upside right or upside down. 2.5-year-olds are mostly holding them upside right. But what they're doing, the images they project to themselves are images of the object with the major axis extended in the line of sight and then rotated around that. That's the view they see, okay? They're rotating it around the major axis. That's what these smears are, okay? You know, because they're rotating around the major axis. Now, you could ask whether this is a hand-holding bias. That'd be interesting if it was, but it's not. We have put these objects in spheres and given them so that holding is equipotential to the view. And what you find is that babies are better at making sure they see rotations around the major axis, okay? So it's a visual bias. And we're now doing studies with 6-month-olds in which we're asking what they can learn and how long they look at objects, depending on the degree to which the rotations they see are rotations around the major axis or not. And I believe 6-month-olds are going to show this bias visually. That study is not done yet. Okay. So the views, they're self-generating a particular kind of data. These aren't random samples of running around taking pictures or even random views on the viewing sphere of these objects. Okay. They're biased and they're structured. We know that these biases and the variability in the input predict object name learning and predict category generalization by the infants, okay? So in one study, how varied the views a child created determined whether they actually learned the names of those objects and it predicted their later vocabulary growth, suggesting children might differ in the quality of the views they show themselves. And we've also looked at the, we've also looked at the range of similarity from the views generated of a single instance of a category when children are playing with it, when toddlers, these are again 18-month-olds, toddlers are playing with an object. And we find a characteristic structure that we're still working on understanding. These are just the similarities of the images, the cropped images of the object to each other, projected onto a 2-dimensional space. But what we consistently find is that there is kind of a core similarity. Lots and lots of images are very, very similar to themselves. These are kind of things around the planar view and rotations of the major axes, but there's lots of odd stuff out there too, okay? And so understanding the role of that structure is something we are, in terms of learning, is something we are very, very interested in. All right, so coming towards my end and trying to move on time here. So what I've told you is, first of all, what the developmental trajectory is, just to keep that in everybody's mind. It's like, feels like a totally different set of studies. But babies move from being piecemeal recognizers of common categories in terms of category-specific features to ones based on shape. And that when they are able to recognize objects based on sparse and abstract information about the relational structure of the geometry of an object, that's when they start showing the shape bias. And that's when vocabulary, noun vocabulary, really begins to skyrocket. So you go into the natural statistics and you say, what are in these natural statistics? And what are in these natural statistics suggests that the individual object is the unit of learning. That it's not about seeing a vast number of very different cups or shoes or houses, but rather kind of small set and pervasive, really massive experience about 1 or 2 unique instances. All right, so how do we explain all this? All right, let me just review where we are. Vision begins with 2D images projected to the eye. I think that's where we need to start in solving all problems about visual recognition. Children have pervasive, extended in time experiences with individual unique objects in which they experience and actually play an active role in generating many highly variable projected images that are also biased. The data is not just all over the place. The relation between those images that are projected to the eye as they go about their daily life, what we call the proximate stimulus, that's what actually comes into the system, and the objects we perceive, the distal stimulus, are complex, but they are lawful. There's an ancient big literature on object constancy. They're lawful with respect to the properties of light and 3D object shape. So what I propose is that children learn the principles of shape for individual objects, and that this is the foundation for their rapid learning and generalization of real-world categories. And I'd like to suggest also that the learning that we're talking about here is generative. When children, it's not discriminative. When children are learning about their sippy cup, those massive number of experiences with their own sippy cup, upside down, in the dark, in the light, with the colored lights reflected from the TV on it, half covered by the dog, upside down in the dishwasher. They're not saying, is this my cup or is it a bowl? They're not forming boundaries between categories. They're saying, is this my cup? Okay. It is about the properties of the cup, generating the things that can be in that category. I don't think it's about boundaries at all. All right, so here's my hypothesis. My hypothesis is that the variable images projected from one object during active vision are constrained by and thus inform the visual system about object shape, and that they support the recognition of that object, the individual sippy cup, let's say, under challenging visual conditions. But once you can recognize that one object, the sippy cup, under challenging visual conditions, you must have abstracted something about the sippy cup shape. And if you have extracted something about the sippy cup's three-dimensional shape, then you are likely to be able to apply those same recognition abilities, recognizing from all different kinds of views, some shape similar thing, let's say a slightly different sippy cup. But this, after all, is a category. You now know those two things in a sense. You may not know the name of them, but you recognize them in the similar way. Your system already has them as a category because it has the shape principles for the sippy cup that extend to shape similar things for relating all the projected images, the proximal stimulus to the distal stimulus. And this idea then is that what this gives you is it gives you the abilities that we see emerging between 18 and 24 months, the ability to recognize objects from sparse representations or abstract representations of their geometrical structure. And that is what allows you to generalize categories immediately. So if this hypothesis is right, we might want to ask, what is the learning mechanism? And I think, again, we want to look to the natural training data for the answer. Okay. So here are the things I think about. Okay. I think that really for the learning of object constancy, which I am proposing, is the solution to all of these problems, the shape bias, shape recognition, shape representation. One of the things we know is that the input is self-generated, that it is biased and structured, okay? It's not sampling every possible image you could have of this object. There are constraints on it. And if there's constraints on it, there may be some principled structure in there that is discoverable. The second thing we know is that these are experiences in time, that what babies see are smooth, continuous change in an image. What I'm showing at the bottom of this figure is one play session, 10 minutes long, in which a baby was playing with an assortment of potentially 30 objects on the floor. Baby could play with them. These were 12 to 2-year-olds, 12 months to 2-year-olds. But this is one child. Baby could play with that object, any object of 30 hanging out on the floor, as long or as little as they want. What this shows, this figure shows, is pixel to pixel similarity of one image to the next successive image. This is at 1 hertz. One image to the next successive image, okay? And what you can see is they're highly, highly similar, dark blue. And then they switch an object, you know, ball rolls away and they turn their head to something else, okay? And you see a rapid shift. But there are long periods of smooth, continuous, slow change in these images. So this long, slow change in these images potentially provides a learning signal in itself, okay? And there are some interesting algorithms out there doing this, LeCun, some others, that are looking at using the similarity, breaks in the smoothness of the change is when you say it's a new object. Otherwise, you just aggregate with what you've just seen. All right, now kids don't do this. This is the other thing that I think is probably important, that kids don't do this just for their one sippy cup. They're building these same kind of principles of shape for their sippy cup that they see a lot of, maybe their own teddy bear that they sleep with that they see a lot of, the spoon that they are being fed with, the window next to the table at mealtime, the family's pet dog, the tree in the yard. So they're doing this for a small set, but a number of categories that are pervasive in their visual experiences, that these may bring kind of general principles, serve as a sort of basis function maybe, or give rise to the general principles of shape and shape similarity. And that allows them to learn any category at will, to build a category of tractors from a single John Deere. All right, so my next steps, okay. Well, I'm a developmental psychologist. So what I'm going to do and what I'm busy doing right now is doing experiments to directly test this hypothesis by giving children longitudinal experiences with specific novel objects that are more and less movable, that they can see more and different views of, and then to test how well they can recognize those objects in hard visual conditions. How well they can generalize a recognition of those objects in hard visual conditions to shape similar objects, and then their ability to form categories. And in this work, we are working with 17-month-old infants who are at the front end of all this, so we can hopefully move it forward. Now, what one would really like to do, of course, is given these ideas, is try to build some kind of learning machinery that really could specify what the learning mechanisms, sort of range of architectures, loss functions that could take these kind of data, okay, and end up with rapid learning and generalization of visual categories from very few experiences. The way we're approaching it with my collaborators, Jim Ray and David Crandall, is we're focusing on principles of learning about object shape from smooth, continuous, self-generated experiences. We aren't there yet, but that's what we're trying to do. All right, so I'd like to thank you for having me. I hope you found all this useful. I'm really interested in what questions you might have to ask. And I want to point out just several people here. Elizabeth Glerkin, whose dissertation I talked about, Haydar Reyes, who was brilliant, okay? I'm going to be doing very interesting things. And my collaborators, Cheng Yu, David Crandall, on this project in particular, Cheng Yu, David Crandall, Jim Ray, and Alfred Pereira. Okay, thank you very much.
Thank you so much for that talk. It was really, really fascinating. And I find this work incredibly inspiring because it suggests a learning paradigm that's so completely different from everything that we do right now in computer vision. And that's just really exciting because it makes, well, first of all, there's a proof that it actually works because of what we see humans doing. And the second is, I think that our current learning mechanisms aren't working particularly well. So I think that there's a need for a change. So I think we should take some time for a couple of questions. I'll maybe just start with one for myself, which is that when I think about moving from the current learning paradigm that we mostly use with like a web source data to something like what you're proposing is this sort of more natural, better learning mechanism that infants use, is very daunting because at least three things seem that they might have to change. One is the statistics of the images. So this sort of egocentric focus on a small number of instances, but seen extensively under very different conditions. The second is embodied control. And the third is this multimodality where occasionally you hear things being named. It feels hard to try to do all of those at once. And I'm curious if you have any prediction about whether it's possible to maybe only incorporate the different image statistics and forget about the embodied and auditory aspect of it.
So actually, I think you could, one, forget naming. I think it's a small player. And honest to God, I think the way to go after it is to use proximity in time and similarity as the learning signal, okay? So we've been doing a little bit of stuff with a graduate student, Violet Zhang, who was, well, she was an undergraduate, and now she's ran off to Stanford to work with Yamans. So we've lost her. But where we were working at the idea, going from the baby's images, really just trying to look at pairwise images and say, if they're close in time and they're similar enough, you say they're the same object, okay? And see how far we could get with doing that, okay? And we could actually get pretty far, okay? And that they would generalize to new views of those objects, and they would generalize, the algorithm, okay? Would generalize, it was kind of a Siamese CNN kind of thing. It may not be perfect, but it would but it would generalize to similar, not far weird members of the category, but roughly kind of similar members of the category. And since children's advances are incremental, that seems okay to me, okay? But it's a start, but that's where I would put my money, okay? Is in the proximity in time, and similarity itself as the signal for learning. But it's also okay, so data is highly biased, okay? When you look at the viewing sphere, you're not seeing all the views. And you also see what people, you also see a lot of occlusions. I think those might be important for pulling up the shape. And you see a lot of lighting changes and egocentric images that you don't ever see in the, kinds of photos off the web.
Yeah, thanks. That's encouraging, I think. So maybe we have time for one more question.
I just got the answer from the previous, I had a very similar question of okay, how big are the videos that we need for to start developing similar mechanism, but your answer about experiment with just 2 images and the proximity, that kind of answers it already.
Yeah, well, we had more than 2 images for a single object. We would have, I don't know, 1,000, but it wasn't 1 million, okay? It wasn't as many as the baby sees.
Okay, all right, great. Yeah, again, thank you so much for joining us. Really very interesting, inspiring.
Okay, well, thank you for having me, and maybe you can find some solutions for me.
Yeah, we'll let you know.
Okay, thanks.
Great. Okay, so next up on the agenda, we have the invited research talk. And so this will be presented by Cheng, Zhang. So let's see, I think I see you in the participant list.
Yeah. Yeah, I know.
I can't seem to undo this.
Sometimes the Zoom screen sharing thing hides.
I can't find it. Okay, I'm going to go out. Just let me go.
Okay.
Okay.
Sounds good. Okay, we see your screen now, Cheng. Thanks.
Okay. Thanks, Ross and the organizers for inviting us to give this talk. And hello, everyone. My name is Cheng Zhang. We are from Team Ohio State University. And I'm super excited today. So we have seen several great talks and ideas on how to solve LVIS. So in this presentation, we will take a different route to resolve this problem. That is, can we leverage object-centric images to help long-tail object detection? Again, let's review what's the challenge here. What's the fundamental challenge here? In LVIS, we are actually dealing with scene-centric images. That is, those images capture scenes or events. The objects inside are usually small with complex background. Moreover, with such a huge number of classes, we just don't have enough instances for every class. For example, here, you can see a lot of tennis rackets, but we don't have sufficient bird feeder instances to teach the machine to understand the appearance of bird feeder. So, however, let me ask one question here. Is bird feeder really a real class in our life? Let's do a simple test. We can go to Google Images, type in bird feeder. Here is the result. We actually can see a bunch of images and even more. But if we take a deeper look to compare those images, we can see, well, these images actually just contain very few or just one salient object. We can call them object-centric images. So what we argue here is that, well, although we may not have lots of images with bird feeder in certain contexts, just as what you see in LVIS, we can easily get images when bird feeder appears alone, right? So moreover, beyond this kind of Google images or web images, there exist other good resources like ImageNet 22K. Okay, let's go back to check this distribution again. Indeed, we can find nearly all the corresponding classes in ImageNet 22K. If you look at the number of instances in ImageNet, they are no longer long tail, like the black dots here, especially for real classes. So our main idea is that can we leverage these abundant object-centric images for long-tail object detection? Well, you may ask, is this idea feasible? So we believe yes. Actually, just remember the first time you go to Zoo, you can recognize author, right? So this is because you probably have learned author in object-centric images from books. So let's recall Professor Smith's talk. Baby learns individual concepts from individual objects at home, and then can perform perception in the scene. So that's why we think this should be a very natural way to improve long-tail object detectors. Well, to use these object-centric images is by no means trivial, right? There are actually several challenges here. First of all, as you can see here, object-centric images just don't look like scene-centric images. There is a domain discrepancy. The second challenge here is that object-centric images don't have bounding boxes annotations. So how can we use them to train an object detection or even instance segmentation model? So we propose a very simple method called mosaicos. Our method has 4 stages. First, we train a detector. Just use LVIS scene-centric images. In this stage, this stage is just like you train a baseline detector on the original LVIS training dataset. So at the same time, we will prepare object-centric images, which initially have no bounding box labels. We will try to annotate pseudo labels on each of them. Actually, adding pseudo labels is nothing new here, right? So we can search a bunch of related work. For example, this image is Turkey from ImageNet. We do know its image level label. And then we can apply weakly supervised methods to create pseudo labels like this one. It may contain certain noise. And surprisingly, in this paper, we figure out even using simple heuristic methods by placing 6 fixed locations, including center crop, 4 corner crops, and the whole image already performs pretty well. So we will use this one as our default setting in Mosaico's framework. So after getting the pseudo labels, our third step is to mosaic those object-centric images to make each of them a little bit smaller so that the whole mosaic images can cover multiple objects such that they look more like scene-centric images. We then use these mosaic images together with pseudo labels to fine-tune the detector pre-trained on LVIS. So you may know that our Mosaico here is totally different from Mosaic in EuroV4, in which they only mosaic scene-centric images that are already in LVIS training set. We believe what we are doing here can help detector to learn more appearance of different objects. This is very important. But at first glance, you may think, oh, this detector trained on such artificial mosaic images may not perform very well on real LVIS images, right? So our last stage is to fine-tune the detector on original scene-centric images, just like what we did in stage 1, treating LVIS as a downstream task. We then get a final detector. So in stage 4, if we do have mask annotations, we can fine-tune the detector for instant segmentation purpose. Okay, let's take a look at our experiments. We validate our methods on both versions of LVIS. We mainly use ImageNet 22K as object-centric sources, which can cover most of the LVIS classes. We also retrieve 100 Google images per class as supplementaries. We use 2x2 mosaicing like this one, and fix 6 locations as pseudo labels. We evaluate on standard AP and also report results with new evaluation metrics used in this year. So all the results are reported on validation set, and all models are trained with using the same code base. Let's first look at the results on version 0.5. So in the task of object detection, we show our method can improve object detection by a large margin. Here, the blue one is the baseline, and the orange one is our method. We can improve all classes. Specifically, we achieve 60% relative improvement on real objects. Our method can further improve instant segmentation, achieving 23% relative improvement on real objects. As you can see here, for both tasks, mosaicos can notably improve real classes without sacrificing frequent ones. We then move on to LVIS version 1. So as you can see here, with ResNet 50, we got similar improvements. These improvements are consistent even using stronger models, like ResNet 101 and the ResNext 101. Although the baseline accuracy here gets higher, we still can see a decent improvement. Here we further show the results with this year's new metric, AP-Fix and boundary IOU. You can see that Mosaicos is metric agnostic. It can improve all classes. Okay, so far we see our method is very simple, but it works pretty well. We want to analyze which components really lead to improvements. Let's look at this framework. Specifically, we want to ask the following questions. First, we want to know how to generate pseudo-labels. Second, does having mosaicing help? Third, where to use object-centric images. That is, instead of using object-centric images in stage 3, can we treat them as classification data? That is, to pre-train the backbone here, just like ImageNet classification task. Finally, we want to know if we can combine stage 3 and stage 4 to train these two domains images together. Let's try to answer these questions one by one. We first show the result on pseudo labeling. Here is the result of our baseline and the fixed 6 locations. We also try a weakly supervised method, which can get much more accurate pseudo labels like this one. However, we can see fixed 6 locations already got very decent performance. So in the following, we will focus on fixed 6 locations to make our pipeline very clean. Next, we study the effect of mosaicing. Again, the blue one here is our baseline. If we include object-centric images, but without mosaicing, we can see an improvement here. However, this is way smaller than pseudo-scene-centric images by mosaicing. Now let's move on to another question. What is the best way to use object-centric images? So in this paper, what we do here is we annotate the object-centric images with pseudo labels and then treat them as detection data to fine-tune the object detector. But as I mentioned before, we can also use object-centric images with image level label to pre-train the backbone, like ResNet. Here we want to know how to compare these two strategies. Fortunately, we found that there are 176 overlapped classes between ImageNet 1K and the LVIS validation set. So that is, which means that the corresponding ImageNet images used by mosaicos are already seen by pre-trained ResNet backbone. Here is the result. Surprisingly, we see that mosaicos still leads to a notable gain for these classes. This suggests that the importance of learning downstream tasks directly using those object-centric images. You know, given the strong performance from transformer, I do expect mosaicos can be compatible to even stronger transformer model. We then investigated 2 ways to train with pseudo-scene-centric images, starting with the baseline detector. The first way is to fine-tune the detector with scene-centric images and the mosaic images together. Unfortunately, the performance drops. Another one is our multi-stage strategy. We first fine-tune with mosaic images, and then with original scene-centric images. We see a significant improvement. This indeed demonstrates the benefit of multi-stage training. The final stage adapts the detector back to the true scene-centric images in LVIS. Indeed, we found this kind of multi-stage training is very effective in learning with noisy data. So actually beyond object detection, in one of our recent multimodal learning research, we show a similar phenomenon or power of multi-stage training for virtual question answering. So please take a look if you are interested in it. So in summary, in this work, we propose simple mosaicos framework to leverage object-centric images for long-tail object detection. on scene-centric images. You may go to our paper for more details. And finally, I would like to take 1 minute to trigger the discussion about evaluation metrics. We want to rethink about the usefulness of conventional AP. In conventional AP, we put a cap on how many predictions a detector can make per image. For example, 300 in LVIS, 100 in COCO. We think such an evaluation metric still makes sense when on the setting of considering each image alone, especially on online detection like auto driving, where the testing frames come in one by one, right? And in our upcoming LVIS paper, we show that if the conventional AP is the evaluation metric you want to optimize, just try post-calibration method. It is surprisingly effective. Okay, I will stop here, and I'm glad to take any questions. Thanks.
Right, thank you very much. That's an interesting talk. I know that a lot of us have been curious for a while, the degree to which you can use object-centric images in order to improve on LVIS rare categories.
Yeah.
So do you have time for a question if anyone from the audience would like to ask one? Okay, well, if not, then that's also okay, because I think we're running a little bit behind. So in that case, we'll move along to the final invited talk of the workshop. So this is from the first place team, team FuXi-Fresher. And unfortunately, they're unable to join us live today, but they did send us a pre-recorded video. So I will go ahead and play that.
Hello everyone, my name is Cheng. Our team name is FuXi-Fresher, and we are from Tencent YouTube Lab. I was lucky to participate in the LVIS challenge and was invited to do this presentation in the workshop. Due to that time limitation, we cannot participate online. So here, we would like to show a video of our work. The topic of our report named Distribution, Balanced, and Boundary Refinement for Large Vocabulary Instance Segmentation. Our report is introduced from the following 3 aspects. The first part is overview of LVIS challenge. LVIS is a famous benchmark dataset for large vocabulary instance segmentation. It contains about 2 million high-quality instance segmentation annotations in more than 1,000 categories. Compared with the COCO dataset, the LVIS dataset has a long-tail distribution which is more similar to the real world. In addition, compared with last year, this year's evaluation metric has been changed from mask AP to boundary AP, where boundary AP pays more attention to the accuracy of the edge of segmentation results. Obviously, this year's LVIS challenge has higher standards for mask and boundary quality. Here is our approach. We divide it into strong, balanced baseline, distribution balanced, mask and boundary refinement, and finally, learning strategy. The first is our strong baseline. Our final framework is HTC without the semantic head. It is a classic and powerful instance segmentation architecture. We use SwingL as the base backbone. For further enhancement, we use CB9 version 2 to group 2 identical SwingL through composite connections. And in order to deal with the problem of long-tail distribution, we first balance the dataset using repeat factor sampling, balanced copy-paste, and balance the mosaic. Repeat factor sampling can increase the number of the images containing the tail categories in the image level. But balanced copy-paste can directly increase tail instances. This avoids mixing of head instances. In addition, we adopted the balanced mosaic proposed by the second place last year. Then, we also modified the loss using seesaw loss. It can dynamically suppress the excessive negative sample gradient on the tail category. Next, we introduce the work in boundary refinement. Because of the pooling operation and the 28 multiply 28 mask representation size, the instance mask generated by the HTC model is still very coarse. This year, the LVIS challenge has high requirements for the accuracy of the boundary. We use the refine mask to replace the mask head of HTC. Refine mask has integrates fine-grained features and refine masks stage by stage. In this way, we can obtain a higher quality mask prediction. It is worth noticing that we only replace the last mask head of HTC with the refined mask head. We also used mask scoring to rescore the final mask, and it can adaptively learn from the mask quality. This page introduces the learning strategy during the training and testing phases. In the training phase, we set the batch size to 16. We train all models for total 20 epochs. The learning rate is set to 1/10,000th and 5/100,000th, corresponding to single swing L backbone and CB Knight Warren-2 backbone, respectively. The learning rate decays to 1/10th of the original at the 16th and the 19th epochs. The weights of all models are initialized with ImageNet pre-trained model. In the testing phase, we use test time augmentation to fuse the prediction results of multiple resolutions. At the same time, we have increased the number of output instances of each image. In the experimental part, we first introduce a weak baseline and a strong baseline. For weak baseline, we directly use repeat factor sampling and seesaw loss to solve the problem of category imbalance. And we directly adopt swing L in the weak backbone. Although some methods are effectively on a simple big backbone, it may not work on a stronger backbone. Our weak baseline achieves 39.1% mask AP. After adding balanced copy-paste and the mosaic, the mask AP further increased to 40.8%. Subsequently, we replaced the backbone with CB9 Warren-2. It essentially combines two swing L. In the end, our strong baseline achieved a mask AP of 43.1%. Subsequently, we introduced the refine mask and mask scoring modules on the basis of strong baseline. Before introducing this part, let's take a look at the picture on the left. It is the AP curve of the strong baseline on the validation set. It can be seen that its AP curve fluctuates greatly. So we use exponential moving average to smooth the model. We visualize the AP curve of the model on the validation set after adding exponential moving average and the refine mask. We can see that the curve is indeed much smoother. Surprisingly, we found that mask AP tended to converge in the 6th epoch. Therefore, we adopted the early stop strategy and used the results of 6 epoch as our final results. At the same time, the performance gap between AP rare, AP common, and the AP frequency in the 6th epoch is smaller. Then, we use mask scoring to rescore the predicted mask. This further improves the accuracy of the model to 49.2%. Finally, we introduce some tricks in the testing phase. First, we use the test time augmentation strategy, which brings a 1.3% improvement. In addition, we increased the number of instances predicted for each image according to the hint of LVIS API, which also has an improvement of 1.2%. Due to time limitation, we did not make an inference of the model with both task configs mentioned before, but we have these shown results in the test challenge set. Thank you for watching.
Okay, all right, so that concludes all of the presentations for the workshop today. And we're going to have a panel discussion now as the final event. So I'll go ahead and share my screen again to pose a few topics that we can consider for discussion. Okay, so I guess if you're here and you would like to participate in the panel discussion, and this includes both workshop organizers and also any participant, I would encourage you to, if you're comfortable, start your camera so that we can see people who are here and interested in discussing. Okay, so I think that I'll probably act a bit as the moderator and hopefully encourage discussion from other people. So the first topic that I'd like to raise is, this is actually maybe intended more for the people who participated in the challenge or who have recently been working with LVIS. And that is, what's your experience with the fixed AP metric? Did it make participating this year too difficult because of the computational demands, et cetera?
Okay, maybe I can say something. I think the fixed AP make the inference time much more longer than before, right? This is what I got.
Okay, yeah, so it's definitely clear that there's some challenges in terms of both inference and evaluation time. And so I guess that one thing we'll have to consider when trying to decide whether we make this the official metric or not is whether that cost is balanced by the gains of making AP what it was originally intended to be, the category independent metric.
I think, yeah, it's not just the evaluation part, right? Like the inference part is also like almost as bad. Like if we're talking about some methods like scarce CNN, it's all right because we know that it's actually like with like threshold that we put at 0.1, it's actually will produce like 2,000, 5,000 masks per image, something like this. When we're talking about some experimental methods that are like significantly different from scarce CNN, it's like easy to expect like 300,000 detections per image easily, because it's not well fine-tuned. There is a threshold somewhere, but we don't know. And it's like a lot of playing. And like as soon as you have a model that like produces like thousands of masks per image, then it's like, then it's a real bottleneck, and not even like not to go into evaluation, but like how to get this like 10,000 category, like 10,000 detections per category. That's already an issue. And I think like then we were like introducing fixed AP, we weren't thinking as much about this kind of settings, because with mascarcine, that wasn't kind of an issue. But with new methods, it's actually a huge issue.
Yeah, so there are, of course, some algorithmic things that you can try to do, like Achal's implementation using a priority queue and adaptive threshold that you first estimate with the lower cost model by turning off various heads. But again, that solution depends somewhat, it's not super specific, but it does exploit some properties of mascarcine and may be more or less adaptable to other methods.
So one suggestion. So I think if, for example, if the evaluation metric changed to fixed AP, I think you may also like better to provide kind of inference script or something like that. So like they'll that participant easy to do this specific type of inference, like making sure each category has certain number of prediction.
Yeah, so Achal does have a nice implementation of this, but I guess the kind of issue is that it's somewhat specific to both Detectron-2 and mascarcine. So the idea of providing a generic efficient inference script that kind of works for everyone's code and everyone's models is probably not really possible. But I agree, in principle, it would be very nice.
I have a different perspective according to the evaluation metric. So first of all, thanks for organizing the workshop. So I think the metric is depend on the application scenario, because AP-Fix is assuming that class should not be interdependent. And I think this is best fit for the application that the user has a specific vocabulary at hand during test time. But fixing the number of objects per image is like the user just want to detect general objects, and he want to see what objects are there in the thing without a specific goal in mind, what object you want to detect. I think both are, for me, it depends on, we believe, which application scenario is more general.
Yeah, I have the same theory. That is, maybe these two, I think both AP and AP-Fix are fantastic. So the main difference is here, probably AP-Fix is more focused. It's more, the purpose of AP-Fix is that we want to deal some retrieval setting. That is, we already have a bunch of evaluation images. We want to test the model on it. But for AP, just as I mentioned in the talk, that is, if our settings are online detection, so we want to test image one by one, more like a transductive setting. So we probably also care about the AP. So is there any way we can encourage people to report both of them in the paper or in the challenge? That is, we know that sometimes we can game the AP, right? So just like some literature, we can game the AP. So that's why not only AP, you also need to report AP-Fix to test the ability of your model. Thanks.
Yeah, so maybe I'll put Achal on the spot and see if he has any comments to add to this.
Yeah, no, I think the inference is definitely annoying. I think one thing I'll say is, so the initial implementation that we did was pretty specific to mascarcine, where we like turned off the mask heads and things like that. I actually think that even if you don't do, so there's two levels of optimization. There's one optimization where you keep a priority queue. So you only ever keep around 10,000 detections for any class. And as you go through the data set, you have to run your model less and less because your queue has filled up. And in fact, at some point, your inference will actually come faster per image than it would with the original AP because of that. So that's the first optimization. And that one is actually pretty generic. The only part that's not generic is like every framework has different ways of setting thresholds. So, for Detectron versus MMDet, that script needs to be modified. The second level of optimization was you can turn off the mask head initially so that you don't do some expensive things when you're still figuring out thresholds. This one is actually not super, super important because it really only hurts you in that initial bit. So I think it is possible to write a script that is generic across models within Detect_Run2, and then another one for MMDet, and then another one for a different one. But I get that, like, this is not ideal. I mean, this is definitely much more complicated than, you know, having a single threshold per image.
Sorry, like super dumb question. I do not understand. Why is it faster? Like, why is it getting faster?
So once you have, let's say you run through half of the data sets, you can basically set your threshold now adaptively to say, okay, well, you know, the lowest confidence person detection on this image is 0.5. The lowest confident person detection in my 10,000 queue is 0.5. So now I should never look at things that are below 0.5 confidence per person. So
Yeah,
you want to run, sorry, go ahead.
I still need to do the inference to know the confidence score for all my proposals, you know?
Yeah, I guess this is, okay, yeah, that part becomes framework dependent. So at least a lot of models, like if you set a threshold of 0.5, you'll run like one part of the model and then you'll stop early on because now you don't have to run the mask head, you don't have to run, and that is kind of built into a lot of models. For example, in any model, if you set the threshold to 0.2 instead of 0.1, the whole inference will run a little bit faster. So you can see this with probably any detectors. If you set the threshold to 0, it's going to run really, really slowly. So there is, you know, every detector I think will probably have some optimization in order to ignore low confident predictions, where low confidence is determined by a threshold. And so as that threshold goes up, you have to do less and less of the expensive computation. But yeah, I think I would love if there was a way. I mean, I think like the thing that ends up being a question is how much is the gameability a problem? I don't think I have a clear answer for that, so I don't know if I have I don't have a strong opinion at this point on is the fixed AP critical, or is it something where like, okay, well, no, it's gameable, but we can, you know, live with it.
Yeah, thanks for the comments. Yeah, so I guess that we'll have to do some soul searching over the next weeks and months to try to make a decision about whether we want to adopt fixed AP as the official AP. Okay, so we've been focusing on that side of the metric change. There's also the boundary AP instead of mask IOU based AP. That is maybe less of a controversy, but I'm curious to hear if anyone has any opinions for or against it based on your experience.
Can I provide some biased opinion?
Well, I was about to say, it sounds like everyone loves it. Go ahead, Alex.
Yeah, I thought that like it was interesting to see methods trying to address it like this year, you know, like this like 4K VAT model. I doubt this kind of approaches would appear if we want to introduce this metric like last year. And this is like, for me, this is nice, right? That means like we basically as like Ross was saying in the very beginning, like then we were talking about AP and the thresholds and like how like is this object detection or like object segmentation? No, it's small, like right. It's somehow like relevant to like improving AP to solving object detection, but it's not really that like the final goal. So like finding some of these places and like pushing people to innovate there seems to be good, and we actually saw that this is happening. I don't know whether we should stick and do it like maybe like, you know, every year we should shuffle it a little.
Sorry, is there a downside to boundary AP? It sounded like it was a clear win. So, I mean, is there an argument for going back to mask IOU ever?
I think it really depends. Like in the realm of Coco images, an LVIS annotation, maybe we are at the stage where like basically like we're very good at like predicting blobs for large objects. Like, and we did the analysis in the paper, right, showing that like this is actually very rare. Then the blob is not predicted, at least with like IAU 50 for large object. So like I think it might not make sense, but at the same time for like some potential other data where our methods are still very bad, and like that's a bit too early to focus on boundaries. Like right now we're at a stage where it's okay to focus on this, but in some other data it might not be the case.
I will also point out that so the boundary IOU requires your data set to actually be very well annotated, like the quality of the annotations have to be really good. And that might be the case for LVIS, but for other data sets, maybe the original COCO and of course other data sets will have lower quality annotations, which make it less feasible to use boundary MAP.
Yeah, that all makes sense. Good points. Okay, so we're generally running a bit over time, so I think I'd like to try to wrap up at 12:15. So maybe we have time to discuss the other kind of main theme in the panel topics here, and that's about the use of additional data. So this year we permitted using ImageNet 22K, and so I guess I'm interested to hear what people think about that, and related to that. Should we allow in the future for using models such as like CLIP or Line that are trained on much larger corpora of weakly associated image and text data? So, okay, maybe I'll try to prompt people a little bit more. Okay, so it's clear that using ImageNet 22K can bring improvements. And I guess from that perspective, probably everyone felt good about it because everyone likes to see their numbers go up. But is anyone like feeling concerned that this maybe somehow is avoiding the original spirit of the data set and the challenge by maybe making it too easy to do well in the rare categories? And maybe we should not allow this data because it kind of prevents people from addressing head-on the original long tail problem.
And maybe I can comment something that is, we have made several efforts on these directions. That is, we try to leverage the ImageNet data, right, to directly detect on it instead of using as a classification data. So as you can see here, so even some classes in ImageNet 1K, so if we use them as the detection data instead of classification in backbone, we can see improvement. That is, maybe it's not totally about the amount of data. It's about how you use this data. This is the key ingredient. Yeah. And of course, we admit that if we can retrieve the images from the website, probably we will largely simplify LVIS problem. Yeah.
I guess there's a philosophical question here with regards to the original purpose of the data set, like you said, versus like what is realistic, and like in the sense that are there actually rare categories which aren't in LVIS, but there actually are rare categories out there where we couldn't get internet data, and if that's the case, then LVIS can be seen as a proxy for those categories. If the number of those categories is actually really small, like if there aren't actually a ton of things where you can't get internet data that looks really similar, then maybe LVIS would be seen as a handicap rather than as a proxy for a real problem. And I don't have a strong opinion on this, but I don't know if Agrim or Ross or anyone else does.
I personally think like I don't think there's like harm in using more data, because like if your problem is to solve long tail or like in its extent like open set recognition, then we have strong evidence, at least in last 2 years, that at least from language side, right, like those people can learn any distribution of new task via just large scale pre-training. So why can't, like, in that sense, LVIS should be seen more of like a test set. And yes, sure, if you actually start collecting images which are rare categories for LVIS, then you probably then you probably are not utilizing LVIS as the way it is meant to be. But the goal is for it to be most like a test set or a test bed for that type of evaluation. So that kind of makes sense to me, but I don't think trying to achieve higher number by specifically collecting more data for the categories which are rare in LVIS is probably the kind of big size data set I'm arguing for.
So it's hard to enforce, but it sounds like what you're saying is if you collected a data set without knowing the LVIS categories beforehand, then it's okay. But if you collected the data,
yeah, if you specifically collect a data set with with like LVIS categories in mind, then it's like a ImageNet or COCO kind of situation, and we already know that that is going to work.
Yeah, I guess maybe I view this as evaluating two different scenarios. Okay, so trying to connect this back to Linda Smith's talk a little bit. Okay, so I think that the problem posed by LVIS does match a real scenario, and that's the scenario in which you have the baby that's just seen one tractor in the field, and at that moment in time, you want to test that baby's ability to recognize new tractors. So there are few shot categories in the sense that like the first time you're introduced to some new category, you've only seen one or a few examples of it. So that's one scenario. Another scenario is, this baby has grown up and become an adult. They've seen the world, they've seen everything, they've seen lots of everything. And this kind of corresponds more to the you get to use all the data in the world scenario, and maybe no categories actually is really few shot anymore. I think both of these are interesting. So maybe it's just a matter of what we want to emphasize.
Yeah, I agree. Like, I think it's more like, are we trying to find a way to scale up object detection? For example, now we are like around 1,000 classes. What's the best way we can scale it up to 10,000 to 100,000 classes without, again, significant human labeling? This is one way, right? The other way is really about, okay, how about in the future, we do have some task that it's really long tail, which means you cannot find other classes. You cannot find other resource to kind of add more instance to tail class. I think there are two extremes. I mean, why is that? Well, it's just about how to scale up without significant labeling. The other is, well, there's real scenario, you are long tail. And I think there are some common ground between them, but they are also kind of different spirits.
Yeah. And I guess personally, I'd like to find ways to encourage the research community to work on both of those, because I think they're both fascinating. Cool, great. All right, so does anyone else have any final thoughts or comments to share before we wrap up? Sounds like that's a no. Okay, so great. Yeah, this was a lot of fun. I want to thank my co-organizers for helping put all this together and for their nice presentations and great analysis. And I'd like to thank all of the presenters who presented throughout the day. And wherever you are in the world, I hope you enjoy the rest of your day or have a nice night's sleep.
Thank you.
Right. Thank you. Bye.
Thanks.